What if the most terrifying landscapes imaginable exist not in nightmares, but in the universe beyond our own? From the relentless heat of Venus, where clouds of sulfuric acid swirl menacingly in a crushing atmosphere, to the volcanic chaos of Io, a moon that continuously reshapes itself through fiery eruptions, each planet and moon presents a unique horror. Picture Mercury, scorched by the sun, where every day is an unforgiving blaze, while Mars holds secrets beneath its dusty surface, perhaps hinting at ancient lurking dangers. Join us as we journey to some of the scariest planets in our universe. Venus presents an incredibly hostile environment for anyone daring enough to explore it. The atmosphere is not only thick and heavy, but it is also composed primarily of carbon dioxide, with clouds of sulfuric acid swirling through the skies. Imagine stepping into an atmosphere that exerts pressure over 90 times that of Earth's, a weight that would crush most human-designed vehicles. Temperatures soar to extremes, exceeding what you might find in an oven when set to high. This intense heat transforms Venus into a place where many materials would simply melt away. Additionally, the toxic clouds create a caustic environment that would corrode equipment in a matter of hours. The thick, cloudy shroud envelops the planet, blocking any view of the surface and creating a constant state of darkness, as if the sun itself could hardly penetrate this oppressive atmosphere. For potential explorers, not only would the physical challenges be overwhelming, but the risk of catastrophic malfunction is ever present, making even the most rugged spacecraft susceptible to these unyielding conditions. The perfect storm of crushing pressure, scalding heat, and corrosive chemicals makes Venus an extreme frontier that tests the limits of technology and human endurance. Venus stands out in our solar system with its extremely high surface temperature, which is hotter than that of Mercury, despite being further from the Sun. While Mercury, the closest planet to our star, can experience scorching heat on its sunlit side, with temperatures soaring to very high degrees, it cools significantly on the dark side due to its lack of atmosphere. In contrast, Venus, enveloped in a thick, toxic atmosphere rich in carbon dioxide, experiences an intense greenhouse effect. This trapped heat results in average surface temperatures that hover around incredibly high levels, hot enough to melt certain metals. When we consider other planets, we find that Earth has a moderate and life-sustaining climate, while Mars, with its thin atmosphere, is much colder. Even in the outer solar system, gas giants like Jupiter and Saturn do not reach the extreme temperatures of Venus, despite their stature. The unique conditions on Venus, characterized by relentless atmospheric pressure and clouds of sulfuric acid, create an environment that could be described as hellish compared to its neighboring planets. Thus, in this planetary comparison, Venus reigns as the hottest planet, embodying a striking lesson in the effects of atmosphere and distance from the Sun. The atmospheric pressure on Venus is truly extreme, creating conditions that are incredibly hostile for any space mission. Picture standing at the bottom of a deep ocean where the water presses down fiercely around you. Now, imagine that same weight, but with thick, corrosive clouds of sulfuric acid instead of water. The pressure on Venus is more than 90 times greater than what we experience on Earth at sea level. This immense pressure can crush spacecraft, making it a significant challenge to develop vehicles that can withstand such conditions. Additionally, the atmosphere of Venus is not just dense, it's also composed primarily of carbon dioxide, with clouds of sulfuric acid swirling ominously overhead. This combination not only creates a suffocating environment, but poses serious chemical threats. Materials used in spacecraft must be specially designed to resist corrosion from these acidic clouds, requiring innovative engineering solutions. Moreover, the temperature on the surface of Venus is another critical factor. It exceeds the temperatures found in most ovens, making any mission equipment more susceptible to overheating and failure. The combination of high pressure, chemical aggression, and blistering heat creates an environment where electronics and instruments can malfunction or simply degrade rapidly. Taken together, the atmospheric conditions on Venus present a formidable barrier to exploration. Any mission needs to account for the harshness of this environment, requiring sophisticated technology and materials that can endure both the extreme pressures and the relentless chemical fury, challenging our understanding of what is possible in space exploration. Venus is often dubbed Earth's evil twin due to the stark contrast between the two planets, despite their similar size and composition. Imagine standing on a world that mirrors Earth in many physical aspects, but is shrouded in a hellish atmosphere. While Earth thrives with life and a breathable atmosphere, Venus presents a hostile environment where temperatures soar to unbearable levels, far exceeding that of a hot summer day on Earth. This is primarily due to a runaway greenhouse effect, where thick clouds of carbon dioxide trap heat, creating a surface that is far warmer than any living creature could withstand. In addition to the oppressive heat, Venus experiences crushing atmospheric pressure that is akin to being nearly a mile underwater on Earth. This immense pressure, along with clouds of sulfuric acid, makes any potential for life on the surface nearly impossible. Furthermore, Venus spins slowly on its axis, leading to extreme temperature variations between day and night, unlike our relatively balanced cycles. While Earth nurtures and supports life, Venus embodies the idea of beauty turned monstrous, showcasing the extremes of planetary science. Thus, by comparing Venus to Earth, we observe the fine line separating worlds that can harbor life from ones that harbor lethal challenges. This juxtaposition fosters a means to explore what makes a planet habitable, making Venus a focal point of interest in our quest to understand not just our solar system, but the potential for life elsewhere in the universe. Mercury is notorious for its extreme temperature fluctuations, which play a significant role in its daunting reputation. Being the closest planet to the Sun, Mercury experiences the most intense solar radiation, leading to soaring daytime temperatures. When the Sun is shining directly on its surface, temperatures can reach levels that would utterly be unbearable for any form of life. However, as Mercury lacks a substantial atmosphere to retain heat, the temperatures plummet dramatically once the Sun sets. This rapid transition from scorching heat to frigid cold results in some of the most extreme temperature swings in our solar system. Imagine going from a heat so intense it could melt metals to a chilling cold that could freeze any exposed material in just hours. This relentless shift creates an environment where survival, as we know it, would be impossible. The extreme temperatures not only make Mercury inhospitable, but also contribute to the formation of its surface. Cracks and fractures formed by the constant expansion and contraction of minerals in response to these fluctuations. Additionally, the lack of atmosphere means that there are no buffer zones to protect the surface from meteoroids. This leaves Mercury exposed to impacts, further reshaping its landscape. The combination of blistering heat and freezing cold, along with the relentless bombardment from space, makes Mercury a formidable and unwelcoming place, driving home the idea that this planet is one of the harshest environments in our solar system. Mercury's surface is a haunting landscape that tells a story of violent impacts and ancient geological history. When we look closely at this planet, we find a plethora of craters, each one a relic of collisions with asteroids and other celestial bodies. What makes these craters particularly eerie is their sheer number and the variety of their shapes. Some craters are deeply pockmarked, while others are surprisingly smooth, suggesting different ages and types of impacts. Among these, the unusual presence of a giant impact basin, larger than any found on Earth or the Moon, stands out like an ominous eye gazing into the void of space. This colossal scar reveals the ferocity with which Mercury has been bombarded over billions of years. To imagine the forces behind such an impact is daunting, massive objects hurtling through the void at astonishing speeds, leaving a permanent mark on this desolate world. Furthermore, unique features within these craters conjure an unsettling atmosphere. Some circular formations are surrounded by dark, smooth material, hinting at volcanic activity or the exhalations of superheated gases beneath the surface. This interplay of impacts and volcanic remnants adds a layer of intrigue and suggests that Mercury is not just a cold, inert world, but one with a dynamic past. The experience of viewing Mercury's landscape is compounded by its extreme environment. With temperatures swinging from scorching heat during the day to frigid cold at night, the surface ends up appearing eerily lifeless, an uninviting realm where everything seems frozen in time. As we delve into the mysteries of Mercury's cratered surface, we are reminded of the planet's role as a witness to the solar system's history. evoking a deep sense of both fascination and eeriness in the face of its silent, scarred terrain. Mercury, the closest planet to the Sun, experiences extreme environmental conditions due to its proximity and rapid orbit. Being near the Sun, Mercury is bombarded with intense solar radiation, leading to scorching temperatures during the day. This can cause surface temperatures to soar to levels high enough to melt certain metals. However, because Mercury has a very thin atmosphere, it cannot retain heat when the Sun sets. As a result, nighttime temperatures plummet, resulting in a stark contrast between day and night temperatures that can swing dramatically. Its swift orbit, which takes just about 88 Earth days to complete, adds another layer to its unique environment. Because Mercury moves quickly through its elliptical orbit, it experiences a rapid change in sunlight exposure. This swift motion means it spends less time in any one position relative to the Sun, contributing to this extreme temperature disparity. Furthermore, the planet's quick rotation, combined with its lack of atmosphere, leads to unrelenting solar winds that continually sweep across its surface, eroding its features over time. These conditions create a barren and inhospitable landscape characterized by craters, rocky terrain, and vast plains of hardened lava, a testament to the planet's violent geological history. Overall, Mercury's close proximity to the Sun and its fast orbit result in an environment unlike any other in our solar system, defined by harsh extremes and ever-changing conditions. Surviving a single day on Mercury would be an extraordinary challenge, one that combines extreme temperatures, relentless solar radiation, and a unique day-night cycle. The atmosphere on Mercury is incredibly thin, nearly non-existent, which means there's little to no insulation against its extremes. As the planet spins slowly, a day on Mercury lasts about 58 Earth days, while a year, or its complete orbit around the Sun, takes just about 88 Earth days. This unusual rotation leads to extreme temperature differences. When the Sun rises over the surface, daytime temperatures can soar as high as a scorching level, hot enough to melt certain metals. Yet when nighttime falls, temperatures can plunge to an unforgiving chill, far below freezing. If one could somehow exist on the surface, shielding would be crucial. A structure capable of withstanding the heat during the day and trapping warmth at night would be necessary. Sunlight would be stark and unfiltered, bombarding surfaces directly due to the absence of a protective atmosphere, presenting yet another hazard. Moreover, the landscape itself is desolate, marked by craters from impacts over billions of years and stretches of rocky plains. There would be no air to breathe, and any surviving on the planet would require a portable life support system to provide oxygen. Water, which is vital for survival, would be almost entirely absent, with trace amounts existing only in permanently shadowed craters near the poles. In this scenario, surviving a day on Mercury would not only mean enduring extreme heat and cold, but also navigating a harsh environment devoid of any earthly comforts. It would require technology and resources beyond our current capabilities, highlighting just how extreme life can be beyond our own planet. Mars presents a landscape that evokes a sense of both beauty and desolation, shaped by its distinctive geological features. One of the planet's most striking characteristics is its vast volcanic plains, punctuated by enormous volcanoes. The largest of these, Olympus Mons, towers significantly above the landscape, dwarfing any mountain found on Earth. Its sheer size and the enormous caldera at its summit give it a stark, forbidding profile. Another feature that adds to Mars's intimidating nature is the extensive system of canyons, particularly Valles Marineris. This colossal canyon stretches for thousands of kilometers, creating deep chasms that carve through the Martian surface. The steep cliffs and the shadowy depths of these canyons contribute to the feeling of an inhospitable environment, one that is both alien and majestic. Additionally, Mars's surface is covered in dusty, reddish soil, giving it a lifeless appearance. The presence of vast, barren plains, interspersed with rugged craters from asteroid impacts, further emphasizes the planet's desolation. These impacts have left behind scars, making the surface look pockmarked and ancient, as if telling stories of a turbulent history. The polar ice caps, composed of frozen carbon dioxide and water, add an intriguing juxtaposition of features. When viewed from a distance, They frame the planet with a hint of cold beauty. However, the unforgiving climate and extreme temperature fluctuations render these areas, like the rest of Mars, largely uninhabitable. Each of these elements, the towering volcanoes, immense canyons, barren plains, and polar ice caps, work together to create Mars's intimidating and desolate character. They tell a story of a planet that was once dynamic and possibly more Earth-like, but now stands as a stark reminder of geological change and the harsh reality of survival in an alien world. Mars has long fascinated humanity, and its story of disappearing water adds a haunting dimension to our understanding of the planet. Once, scientists believed Mars was a vibrant world, rich in liquid water, oceans, rivers, and lakes covering its surface. This past begs the question, what happened to that water? The intrigue lies in the geological evidence that tells of dramatic shifts. Today, we see a primarily dry, dusty landscape marked by ancient riverbeds and mineral deposits that suggest water once flowed freely. Images captured from orbit reveal valleys and canyon systems that appear to have been shaped by flowing liquid. The existence of polar ice caps shows that water still lingers, albeit in frozen form, but the absence of liquid water on the surface raises profound questions regarding the planet's past climate and its evolution. This transformation adds to Mars's eerie allure, painting a picture of a once thriving environment that descended into desolation. The remnants of its watery history whisper tales of atmospheric loss and climate change, processes that mirror our own earthly concerns. Scientists theorize about the role of atmospheric escape, where gases were stripped away, leaving a barren world. Each discovery brings to light a narrative of loss, evoking a sense of melancholy as we ponder the potential for life that once may have thrived there. As we explore Mars, we confront not only the remnants of its aquatic past, but also the broader implications for habitability, both in our solar system and beyond. The thought that Mars was once more Earth-like draws us in, urging us to unravel its mysteries. In this context, the vanishing waters of Mars serve not just as a scientific puzzle, but also as a stark reminder of transformation and the delicate balance required to sustain life. The questions of what could have been make the allure of this distant planet all the more poignant. Massive dust storms on Mars play a crucial role in shaping the planet's atmosphere, creating an environment that can often feel foreboding. Picture Mars as a barren landscape, with fine dust particles stirred up by winds that can reach incredible speeds. These storms can envelop the planet, sometimes spanning entire hemispheres, hiding the rocky terrain beneath a thick veil of dust. The dust itself is not just a nuisance, it has a significant effect on the Martian climate. When storms occur, they can increase surface temperatures temporarily by trapping heat in the atmosphere. This raises the temperature of the air above the surface, creating conditions that can lead to further atmospheric changes. The turned-up dust particles reflect sunlight, darkening regions of the planet, which may disrupt local weather patterns and lead to more intense storms in the future. Moreover, the storms can create a constant state of volatility. The thick dust blankets the terrain, making it difficult to observe the planet's surface features from space or even from the ground. This abrasive atmosphere can affect not only machines, such as rovers, but also any potential future human explorers faced with the challenge of navigating visibility and equipment compromised by fine dust. These dust storms transform Mars into a dynamic, unpredictable world where the atmosphere shifts and changes and the surface is often masked by swirling dust. Understanding these storms is crucial for grasping the complexities of Martian weather and geology, painting a picture of a planet that is as intriguing as it is treacherous. Mars exploration has revolutionized our understanding of the planet, shedding light on the potential for past life forms. Early missions primarily aimed to photograph the surface and gather basic data. However, as technology advanced, missions began to discover tantalizing evidence that Mars might have once harbored conditions suitable for life. One of the most significant revelations came from the analysis of Mars's surface and atmosphere. Data collected showed that water, a critical ingredient for life as we know it, once flowed abundantly, creating rivers, lakes, and possibly even an ocean. The presence of minerals that typically form in the presence of liquid water indicates that Mars had a considerably warmer and wetter environment in its ancient past. Rovers like Curiosity and Perseverance have delved deeper into the Martian soil and rock, revealing organic molecules, which are the building blocks of life. While these findings do not confirm life existed, they suggest that the essential ingredients were present. Furthermore, the discovery of seasonal methane emissions hints at biological activity, as methane is often produced by living organisms on Earth. Spectacular sedimentary structures found by these rovers resemble those formed on Earth in aquatic environments rich with microbial life, reinforcing the idea that ancient Mars could have supported life. Moreover, the identification of specific zones that experienced varied environmental conditions over time provides insight into how habitats might have shifted, potentially accommodating different forms of life. International collaborations and missions continue to refine our understanding, with each new discovery building upon the last. They strengthen the notion that Mars has a complex history and open up exciting possibilities for the existence of past life forms, igniting rigorous scientific inquiry into whether we were ever alone in our cosmic neighborhood. Kepler 438b is a fascinating exoplanet that pushes the boundaries of how we define potential habitability. Orbiting a star located about 600 light-years from Earth, this planet is classified as being in the habitable zone, the region around a star where conditions could allow liquid water to exist. This positioning holds promise, as water is crucial for life as we know it. However, what makes Kepler 438b particularly challenging to our understanding is its size and conditions. It's slightly larger than Earth, categorized as a super-Earth, which means it has significantly greater gravity. This increase in gravity could alter atmospheric conditions dramatically. The concern is that unless it has a strong magnetic field, the planet might suffer from intense radiation and severe atmospheric erosion, particularly if it is close to its star, which emits substantial radiation. This raises questions about whether it's capable of retaining an atmosphere that could support life. Additionally, Kepler 438b orbits a star that is considered a red dwarf, which are known for their frequent and powerful stellar flares. These flares could bathe the planet in harmful radiation, further complicating its ability to foster life. So while it exists in a region where water could be present, the actual ability of the planet to maintain a life-friendly environment is highly uncertain. This dichotomy expands our understanding of habitability by highlighting that proximity to a star and size alone don't guarantee a planet's safety for potential life forms. Thus, Kepler 438b serves as a compelling case for scientists and astronomers, challenging existing models of habitability. It illustrates that the search for life beyond Earth requires a multifaceted approach that considers not only location, but also the nature of the planet's environment and the characteristics of its host star. This complexity reminds us that life may exist in forms we can't yet imagine, shaped by factors we are still working to understand. Kepler 438 is a star that lies over 600 light-years away from us, and it belongs to a category known as M-type stars, also referred to as red dwarfs. These stars are often found to exhibit activity levels quite distinct from those of our Sun. Solar activity, which includes phenomena like solar flares and coronal mass ejections, can have significant effects on the surrounding environment, particularly on any planets in orbit around such a star. In the case of Kepler 438, its solar activity could profoundly influence the atmosphere of any exoplanets within its habitable zone. Imagine a planet in close proximity to Kepler 438, receiving bursts of radiation and energetic particles. These outbursts can strip away atmospheric layers over time, particularly if the planet lacks a strong magnetic field to protect it. The intense stellar winds and radiation might also create a harsh environment on the planet's surface, affecting any potential life forms that could be trying to exist there. Moreover, fluctuations in solar activity can lead to variations in the temperature and climate of the planet. When solar flares erupt, they release enormous amounts of energy, which might temporarily heat the atmosphere, potentially leading to extreme weather patterns. Consequently, the habitability of planets around Kepler 438 may hinge not only on their distance from the star, but also on how dynamic and violent its solar phenomena are. The effects on the atmosphere and potential biosphere are complex and interconnected. If a planet has a thick atmosphere, it might provide some shielding, but if the stellar activity is too intense for too long, even a robust atmosphere might fail to protect the surface. Thus, the solar activity around Kepler 438 doesn't just influence climate, It can define the very conditions under which a planet can sustain life as we understand it. Kepler 438b captures attention both for its potential and its peril. This exoplanet orbits a star similar to our Sun, and its proximity to that star means it likely receives a significant amount of radiation. This radiation can come in various forms, including harmful ultraviolet rays and X-rays, which on Earth are filtered out by our atmosphere. However, Kepler 438b lacks a robust atmosphere, raising concerns about the exposure of any potential life forms to those harsh conditions. The fascination lies in its location within the habitable zone of its star, where temperatures might allow for liquid water, an essential ingredient for life as we know it. The combination of a habitable environment clashing with high radiation levels presents a critical question. Could life, if it exists, adapt to such extreme conditions? Some researchers speculate about the possibility of life forms developing protective adaptations, perhaps thriving in environments that we would consider hostile. This tension between the chance of finding life and the dangers posed by the intense radiation creates an intriguing narrative. As scientists explore Kepler 438b further, it becomes a symbol of the broader search for extraterrestrial life, revealing both the potential for discovery and the harsh realities of our universe. The dual aspects of hope and danger surrounding this distant world continue to captivate our imaginations as we ponder the possibilities of life beyond Earth. Kepler 438b is often highlighted for its striking similarities to Earth, making it a focal point in the search for extraterrestrial life. This distant exoplanet orbits a star that is somewhat similar to our Sun and resides within the habitable zone, an area where temperatures may allow liquid water to exist. The potential for water is central to discussions about life, as we associate it with the conditions necessary for biological activity. However, the parallels between Kepler 438b and Earth begin to unveil a more daunting picture when we consider its environment. The exoplanet is likely much larger than Earth, making it a super-Earth. This increased size can result in a stronger gravitational pull, which affects the atmosphere. A thicker atmosphere might blanket the planet, trapping heat and potentially leading to extreme temperatures. Moreover, its proximity to a red dwarf star poses additional challenges. Red dwarfs are known for their stellar flares and unpredictable behavior, which could bombard the planet with intense radiation. This environment might strip away its atmosphere over time, making it inhospitable despite its location in the habitable zone. Additionally, the tidal forces caused by the planet's size and the star's gravitational influence may lead to substantial geological activity, such as constant volcanic eruptions or tectonic shifts. Lastly, while we can make comparisons based on size and location, the reality is that conditions on Kepler 438b could be harsh and unlivable in ways we cannot yet fully comprehend. The planet's potential to host life is overshadowed by these aggressive environmental factors, turning what might initially appear as a hopeful discovery into a poignant reminder of the challenges of finding a true Earth-like habitat beyond our solar system. Io, one of Jupiter's moons, offers a landscape like no other in our solar system, shaped by relentless volcanic activity. Imagine a surface dotted with active volcanoes that erupt with astonishing frequency, creating a chaotic display of ash and molten lava. What sets Io apart is not just the presence of these volcanoes but their extreme nature. They are fueled by tidal heating, a process where the intense gravitational forces exerted by Jupiter stretch and compress Io's interior. This constant deforming generates the heat necessary for volcanic eruptions that can reach staggering heights. As we explore Io's surface, we're met with a vibrant tapestry of colors, brilliant yellows, reds, and browns, resulting from various sulfur compounds and silicate materials that spew forth during eruptions. The landscape is characterized by vast plains of volcanic deposits and towering mountains formed from lava fountains that can shoot hundreds of kilometers into the thin atmosphere. It's a realm where fierce geological activity constantly reshapes the terrain, leading to a striking and ever-changing topography. The atmosphere around Io is tenuous, mainly composed of sulfur dioxide, creating a unique environment where the ground could be extremely cold, while the volcanic eruptions maintain localized heat. This juxtaposition creates a terrifying yet mesmerizing scene, with plumes of gas venting into space and the threat of lava flows which reshape the surface as they cool and solidify. Each eruption adds layers to the surface, providing insight into the moon's dynamic and tumultuous history. Despite its terrifying landscape, Io is a place of beauty and fascination. It tells a story of relentless geological forces at play, making it a singular jewel in the cosmos, where every eruption reshapes not just the surface, but our understanding of celestial bodies. Making it a singular jewel in the cosmos, where every eruption reshapes not just the surface, but our understanding of celestial bodies. Each volcanic episode is a reminder of the power of nature in the universe, creating a landscape that is both alien and captivating. Io, one of the largest moons of Jupiter, is not just another celestial body. It is a planet-sized testament to the extraordinary gravitational forces at play in our solar system. As Io orbits Jupiter, it experiences intense tidal forces due to the massive planet's immense gravity. These gravitational interactions are so powerful that they lead to some of the scariest and most extreme consequences. One of the most striking effects is the volcanic activity that roars across Io's surface. The gravitational pull from Jupiter stretches and compresses Io, generating tremendous heat within. This heat causes frequent violent eruptions, some of which can hurl plumes of sulfur and other materials high into space. Imagine a world in constant turmoil, with lava fountains shooting up for miles, a phenomenon that has earned Io the title of the most volcanically active body in the solar system. This relentless geologic activity can reshape the moon's landscape in a matter of days, creating a chaotic and hostile environment. Beyond volcanic eruptions, Io's strong gravitational dance with Jupiter also leads to a unique atmosphere that is both tenuous and dynamic. The immense radiation from Jupiter's magnetic field interacts with Io's surface, ionizing particles and contributing to a thin atmosphere that constantly changes. This environment is not only unwelcoming for any potential life forms, but also subject to bizarre phenomena, like the production of colorful auroras and other radiation-related effects that can be hazardous. Additionally, Io is caught in a gravitational tug-of-war with its neighboring moons, Europa and Ganymede. This interaction creates variations in Io's orbit that aren't just fascinating, but can also lead to shifts in tidal heating and even more violent geological changes. The combined gravitational influences push and pull in constant flux, which could one day stretch or even threaten the structural integrity of Io itself. The mighty gravitational forces from Jupiter and its other moons create a wild and tumultuous environment on Io, where volcanic eruptions and atmospheric instability reign. For explorers and scientists, it serves as a vivid reminder of the chaotic beauty of our universe, but also highlights the potential dangers lurking in the shadows of immense celestial powers. Io, one of Jupiter's many moons, presents an otherworldly landscape shaped by its sulfurous atmosphere. This atmosphere, while tenuous, plays a significant role in crafting the moon's eerie and unsettling character. The thick blanket of sulfur compounds, primarily in the form of sulfur dioxide, envelops Io and contributes to its yellowish and orange hues, creating an otherworldly palette that seems almost alien to us. The atmosphere is highly dynamic, influenced by the intense volcanic activity that defines Io. This is the most volcanically active body in the solar system. Enormous plumes of sulfur and sulfur dioxide can erupt, reaching heights that dwarf many earthly volcanoes. When these eruptions occur, the sulfur is expelled into the thin atmosphere, contributing to a constantly changing surface. As the gases disperse and interact with the moon's surface, they create bizarre landscapes filled with volcanic pits, lava flows, and dramatic sulfur lakes, all of which can shift rapidly due to ongoing geological activity. The atmosphere's thinness does not provide the feeling of safety or familiarity that we associate with more stable environments. Instead, it adds an unsettling quality, creating a sense of isolation. The lack of shielding means that radiation from Jupiter floods Io, and the moon's surface bears the scars of harsh conditions, including radiation damage and extreme temperature fluctuations. Furthermore, Io's sulfurous atmosphere leads to a peculiar spectacle of colors that appears alien and ethereal, which further enhances its unnerving presence in space. Each volcanic eruption introduces unique colors and patterns, creating a continuously shifting vista that evokes fear and fascination. This combination of volatile geology and harsh atmospheric conditions fosters a moon that is not only a striking wonder, but also a reminder of the formidable forces shaping the universe around us. Io, with its sulfurous character, remains a place that captures our imagination with its unsettling beauty and dynamic turmoil. Io, one of Jupiter's many moons, stands out as a hotbed of geological activity, making it one of the most dynamic bodies in our solar system. Its extreme volcanic activity is primarily driven by gravitational forces generated by Jupiter's immense mass. Imagine being caught in a cosmic tug-of-war. As Io orbits Jupiter, the planet's massive gravity repeatedly stretches and compresses the moon. This process, known as tidal heating, generates immense amounts of internal heat within Io, leading to eruptions and surface reshaping. The volcanic landscape of Io resembles a continuously changing canvas, with hundreds of volcanoes spewing material onto its surface. Some of these eruptions are among the most powerful known, projecting plumes of gas and molten rock high into the thin atmosphere, often reaching heights much greater than Mount Everest. This relentless geologic activity results in a surface that is constantly resurfaced, an aspect that sets Io apart from many other celestial bodies, which tend to be geologically dead. Beyond its active volcanoes, Io's surface is a tapestry of colors, fiery reds, yellows, and browns, that indicate different volcanic materials and compounds. The lack of impact craters on Io's surface further underscores its youthful appearance. Any markings from past impacts are quickly erased by the ongoing eruptions. The moon's hostile environment reflects its geological ferocity. With temperatures that can plummet to very low levels at night and intense radiation from Jupiter, only the hardiest forms of life might endure. Despite its menacing nature, Io is also a tantalizing target for scientists eager to understand the processes of geological activity and the potential for life in such extreme conditions. Thus, Io not only captures our imagination with its volcanic fury, but also deepens our understanding of the complex interactions at play in our solar system. A pulsar planet like PSRB 1257+12c presents unique challenges that intrigue and daunt scientists alike. To start, pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As these beams sweep across space, they can be detected as regular pulses of energy, akin to the ticking of a cosmic clock. The discovery of planets orbiting such extreme environments raises questions about the formation and survival of these celestial bodies. The primary concern revolves around the conditions surrounding pulsars. The intense radiation and high-energy environment created by the pulsar's emissions could be lethal to potential life forms if they exist. This radiation consists of powerful X-rays and gamma rays, which could strip away atmospheres from any orbiting planets, making them hostile and barren. Moreover, the gravitational forces exerted by a pulsar are dramatically different from those in our solar system. These forces can create extreme tidal effects, potentially distorting the planet's shape or influencing its rotation and orbit in unexpected ways. The behavior of matter in such a dense and extreme gravitational field is not fully understood, complicating efforts to predict the geological and atmospheric dynamics of pulsar planets. Also, the pulsar planet is often a captive audience to its star, circling closely around it. This proximity means that events such as stellar flares could periodically bombard the planet with additional radiation, increasing the challenges for any potential habitability. Understanding how life, as we know it, orbits in such hostile and dynamic environments offers rich insights, but also poses substantial hurdles for researchers. Ultimately, PSRB 1257+12c stands as a testament to the resilience of planetary systems, challenging our assumptions about where and how planets can exist. Studying these enigmatic worlds not only expands our comprehension of the universe, but also pushes the boundaries of astrobiology, inviting further exploration into the diverse environments that might harbor life, despite the daunting conditions. The gravitational force of a pulsar, such as PSRB 1257+12, exerts a substantial influence on its surrounding environment, shaping it in unique ways. A pulsar is a highly magnetized, rotating neutron star that emits beams of radiation. This rapid rotation, coupled with its intense gravitational pull, creates conditions that profoundly impact nearby celestial bodies. As the pulsar spins, its gravitational field acts like a powerful anchor, exerting significant gravitational influence on any orbiting objects, including planets. For PSRB 1257 plus 12c, which is one of the planets in its system, this means that its orbit is tightly bound to the pulsar, resulting in a steady and predictable path around it. The intense gravitational pull not only dictates the planet's orbit, but also affects its physical characteristics, helping to maintain its atmospheric conditions or geological activity. Additionally, the pulsar's immense gravity can create high-energy environments. Pulsars emit intense beams of radiation that can strip away atmospheres from planets if they are too close. This could lead to PSRB 1257 plus 12c experiencing extreme conditions on its surface, including powerful radiation and particles. The combination of gravitational forces and radiation can lead to a dynamic atmosphere, possibly fostering complex interactions between the planet's surface and its surrounding space. The gravitational force of PSRB 1257 plus 12 serves as a major architect of its environment, shaping the planet's orbit, influencing its potential habitability, and creating a distinctive space influenced by high-energy radiation and strong gravitational pulls. This unique interplay makes the pulsar's system a fascinating study for understanding the conditions that exist around such energetic stellar remnants. PSRB 1257 plus 12c, a planet orbiting a pulsar, an incredibly dense and rapidly spinning neutron star, exists under conditions that are unlike anything found on Earth. Imagine a world where your sun is not warm and life-giving, but rather a pulsating beacon of energy, emitting intense radiation and packing a powerful gravitational punch. This environment creates an atmosphere that is harsh and unforgiving. One of the most striking features of PSRB 1257 plus 12c is the extreme radiation it endures. The pulsar emits beams of high-energy radiation that sweep across space, and any body in its vicinity is bombarded by this radiation. This means any surface conditions are intensely hostile. Temperatures could fluctuate dramatically, and the atmosphere, if one exists, would struggle to sustain any form of conventional life. Additionally, the planet experiences constant gravitational fluctuations due to the pulsar's extreme density. The gravitational pull on the surface may be stronger than that of Earth, leading to intense tidal forces. This could cause significant geological activity, including constant seismic events and unusual surface phenomena. The interplay between its orbit and the pulsar's activity creates an environment that is tumultuous, unpredictable, and potentially devastating. In terms of composition, the planet itself could be entirely different from our terrestrial experiences, possibly composed of materials that would be foreign to us. The conditions under which it formed and evolved, influenced by the nearby pulsar, could result in a landscape filled with oddities, including unusual elements that can withstand extreme environments. The combination of deadly radiation, powerful gravitational forces, and potential geological instability makes PSRB 1257 plus 12c a prime candidate for the scariest planet title. Its atmosphere might not support any known life, and those who imagine what it might be like to stand on its surface would be met with a relentless reminder of the power of the cosmos, harsh and awe-inspiring in equal measure. PSRB 1257 plus 12c orbits a pulsar, which is a type of highly magnetized, rotating neutron star that emits beams of electromagnetic radiation. This radiation includes intense bursts of energy in the form of light and radio waves. The presence of this nearby pulsar significantly affects the conditions on the surface of PSRB 1257 plus 12c. As the pulsar rotates, it sends gamma rays and other high-energy particles through space, striking PSRB 1257 plus 12c and bombarding its surface. Imagine the intensity of a constant blazing spotlight. This is what the radiation does, altering the planet's environment. The pulsar's radiation can lead to extreme heating of the planet's surface, likely creating harsh conditions that are unsuitable for life as we know it. Additionally, the bombardment of energetic particles can strip away a planet's atmosphere over time, particularly if that atmosphere is thin. For PSRB 1257 plus 12c, this means that any potential atmosphere could be eroded, exposing the surface to the vacuum of space. Without an atmosphere, the surface would be subjected to temperature fluctuations between intense heat from the pulsar's radiation and freezing coldness during the times it is not illuminated. Furthermore, the radiation can lead to the release of secondary particles and create a number of chemical reactions on the surface. This may result in a surface rich in exotic materials formed by these energetic impacts. Consequently, the combination of radiation exposure and potential atmospheric loss creates a unique yet brutal environment on PSRB 1257 plus 12c, making it a fascinating but inhospitable planet in our cosmos. Titan, Saturn's largest moon, captivates scientists and astronomers with its mysterious and eerie landscapes, particularly its lakes and rivers made of liquid methane and ethane. Imagine a place where the temperatures plunge so low that water exists only as ice. Instead, Titan showcases a complex system of hydrocarbon lakes that resemble features familiar to Earth but are fundamentally different in composition and behavior. One particularly striking aspect is that these lakes and rivers are not merely stagnant bodies of liquid. They are dynamic, constantly reshaping the moon's surface through erosion and sediment deposition. The concepts of weather and erosion here are driven by methane instead of water, as methane rains down from the atmosphere to fill these basins. This creates a haunting parallel to Earth's hydrological cycle, yet inverted, as it drives home the notion that life can evolve in vastly different environments. Additionally, the eerie stillness of these vast liquid expanses cannot be ignored. On Earth, when you gaze upon a body of water, it often reflects life and movement. In contrast, Titan's lakes and rivers are frigid and lifeless, creating an atmosphere reminiscent of an alien world devoid of biological activity. The thick, hazy atmosphere also contributes to a surreal sense of isolation, enveloping the surface in a smog-like shroud that muffles sunlight and distorts visibility. Then there is the phenomenon of surface waves. These methane lakes can experience waves and ripples, much like Earth's oceans, but the implications are different. The friction between the liquid methane surface and the mood-swaying winds can create complex patterns unlike anything seen in our oceans. The sight of these movements, combined with the diffuse light filtering through Titan's atmosphere, paints an extraordinary and unsettling picture. Adding to the eeriness is the possibility of complex organic chemistry happening in Titan's subsurface, where conditions might provide a unique environment for life. The thought that beneath that thick, cold layer of methane lies a world potentially capable of supporting life, even if it's incomprehensible to us, is an intriguing yet unsettling possibility. Thus, Titan embodies a fascinating paradox where familiar processes occur in the most alien of environments, leaving us both amazed and uneasy about what might exist beyond our understanding. Titan, Saturn's largest moon, possesses a thick atmosphere that is unlike anything found on Earth. This dense layer of gases envelops Titan, primarily made up of nitrogen with a significant presence of methane. The presence of such a thick atmosphere creates pressure at the surface greater than that on Earth, affecting everything from potential weather systems to the stability of liquid found on the ground. One fascinating feature of Titan's atmosphere is how it interacts with sunlight. The sunlight causes chemical reactions among the atmospheric molecules, resulting in a rich array of organic compounds that include complex hydrocarbons. These compounds contribute to the moon's intriguing hazy orange color, creating a stunning and mysterious sight. The atmosphere also plays a crucial role in Titan's weather, where methane acts as a key player. This moon experiences rainfall similar to Earth, but instead of water, it rains liquid methane and ethane. Imagine clouds forming in a heavy fog of hydrocarbons, eventually leading to precipitation that creates rivers and lakes on the surface. Titan's landscape is sculpted by these liquid hydrocarbons, which carve valleys and shape features over time. These hydrocarbon rains contribute to an alien environment where organic chemistry can unfold in unique ways. Unlike the water-based life we know, the potential for life on Titan may exist within these exotic fluids, creating ecosystems that could thrive under radically different conditions. The intricate interplay of a thick atmosphere and hydrocarbon rain makes Titan a prime candidate for exploring the possibilities of life beyond Earth, showcasing nature's ability to adapt and evolve in diverse environments. Titan, Saturn's largest moon, presents a fascinating paradox for exploration. On the surface, it appears to have conditions that encourage potential habitability. Thick clouds blanket this world, hinting at a rich atmosphere, while lakes and rivers of liquid methane invite curiosity about the chemistry occurring beneath their glossy surfaces. This unique landscape showcases a complex cycle that mirrors Earth's water cycle, albeit with methane instead of water, making it seem like a celestial mirror reflecting conditions that could support life, or at least interesting chemical processes. However, that inviting appearance belies the serious dangers that await any future missions. The chilling temperatures on Titan hover far below freezing, rendering the environment hostile to human life and most Earth-based technology. Any equipment not specially designed to operate in such extreme cold could malfunction or become obsolete. Furthermore, the surface is shrouded in a thick, hazy atmosphere that limits visibility, complicating navigation and exploration. Enticing as it is, Titan's hydrocarbon lakes may also harbor unknown chemical reactions that could be hazardous. The potential for unexpected interactions with any introduced materials poses significant risks, creating a treacherous landscape for scientific instruments and human explorers alike. The promise of discovery on Titan is undeniably strong, but so too are the potentially perilous obstacles that challenge our quest for knowledge on this intriguing moon. Balancing those qualities will be essential for the success of any mission aimed at unraveling the mysteries that Titan holds. Titan, Saturn's largest moon, is a world of contrasts, where massive size meets a harsh and unforgiving climate. To put it into perspective, Titan is larger than the planet Mercury, showcasing its impressive scale in our solar system. This size is significant because it allows for a dense atmosphere and intriguing geological features, but it also sets the stage for the extreme conditions that dominate its surface. The key to understanding Titan lies in its unique composition. It is primarily composed of water ice and rocky material, giving it a solid foundation. However, its atmosphere is a remarkable backdrop, thick enough to obscure surface details from sight. This atmosphere is rich in nitrogen, much like Earth's, but it has far less oxygen and contains complex organic compounds known as hydrocarbons. These factors create an environment vastly different from our own. Titan's surface experiences incredibly low temperatures, so much so that it often reaches levels that would be considered frigid by Earth standards. At these low temperatures, methane becomes a liquid, forming lakes and rivers that carve the landscape, while clouds of methane rain down from the atmosphere. Thus, Titan is not just a frozen body, it's a place where methane plays the role of water, creating a unique and alien hydrology. This harsh climate poses challenges for exploration. The combination of thick clouds, piercing cold, and a surface covered with liquid methane and ethane offers an environment that is both fascinating and treacherous. Any mission sent to Titan must be equipped to handle these extreme conditions, while also looking into the possibilities of prebiotic chemistry, which has intrigued scientists considering the moon's potential to harbor life in some form. Titan's colossal size and distinct compounds create a breathtaking but stark narrative. It serves as a reminder of the vast diversity in our solar system, where immense bodies can coexist with conditions so severe that they challenge our understanding of what makes a world habitable. HD 189733b is a planet that captivates the imagination with its extreme weather phenomena. Located about 60 light-years away from Earth, this exoplanet orbits its star very closely, resulting in scorching temperatures and intense atmospheric conditions. The fierce winds on HD 189733b can reach extraordinary speeds, much stronger than our planet's most powerful storms. Imagine standing next to a roaring hurricane and then multiplying that intensity. These winds howl at a pace that can reshape the atmosphere itself. Furthermore, what makes this planet uniquely terrifying is the glass rain. This occurs because of the planet's high temperatures and atmospheric pressure, which generate conditions conducive to the formation of silicate particles. In lighter terms, these particles condense into glass-like materials that are propelled by the relentless winds. When these glass shards descend, they do so with incredible velocity, effectively turning a downpour into a deadly, destructive rain. The combination of razor-sharp glass falling from the sky and furious winds creates an environment that is inhospitable to any known form of life. The relentless storms and tempestuous conditions highlight the planet's chaotic nature, painting a vivid picture of an alien world where the elements are not just challenging, but downright hostile. This dynamic interplay of fearsome weather showcases the fascinating extremes the universe can produce, broadening our understanding of planetary atmospheres and their potential consequences. Explorers venturing to HD 189733b would face an array of formidable challenges due to its extreme and hostile environment. This exoplanet, located about 60 light-years away, presents a strikingly inhospitable atmosphere characterized by high temperatures and intense winds. Imagine a world where the clouds are filled with glass-like particles, driven by winds that can reach speeds much greater than those experienced in the fiercest storms on Earth. Such conditions would be disastrous for any exploratory equipment, likely causing severe damage or total failure. The relentless heat on HD 189733b is another significant hurdle. With surface temperatures soaring to levels that could easily melt metals, any materials or technology designed for human exploration would need to withstand extremes far beyond anything experienced on Earth. This would require innovations in heat-resistant materials that are not only durable, but also lightweight for transport. Additionally, the atmospheric composition itself poses challenges. It is primarily made up of carbon dioxide, with clouds of silicate forming in the high, hostile atmosphere. Breathing air is not an option here. Explorers would need to bring their own life support systems. This means providing a reliable source of oxygen and a way to remove carbon dioxide, all while ensuring the safety and stability of their habitat under such oppressive conditions. Navigating the surface would be yet another obstacle. With immense atmospheric pressure and fierce winds, the terrain could shift dramatically, presenting not only visibility issues but also the risk of sudden and dangerous atmospheric phenomena. Explorers must prepare for these unpredictabilities, relying on advanced navigation technology capable of functioning amid savage weather patterns. The exploration of HD 189733b would require overcoming extraordinary technological challenges, from materials that can withstand extreme conditions to life support systems that ensure survival. Each step into this unwelcoming world would be a remarkable testament to human ingenuity, underscoring the resilience and determination to explore the farthest reaches of the universe. HD 189733b presents an extreme environment that drives home its reputation as a foreboding planet. Orbiting very close to its parent star, this exoplanet experiences scorching temperatures that soar well above any severe conditions found on Earth. The intense heat transforms the atmosphere into a chaotic and hostile realm, resembling a furnace more than a haven. Adding to its menacing nature are the planet's violent winds. These relentless gales whip across the surface at astonishing speeds, with gusts strong enough to surpass the pace of sound itself. The combination of high temperatures and these fierce winds creates an inhospitable setting where any form of life as we know it would struggle to survive. The atmosphere of HD 189733b is primarily composed of thick clouds of silicate particles akin to glass. Thus, the relentless wind carries these particles like shards, increasing the danger for any hypothetical explorer. Picture a landscape not just defined by its deadly heat, but also by the fierce cutting glass raining down from the skies. This unique blend of extreme elements firmly establishes HD 189733b as an unfriendly neighbor in our cosmic neighborhood, painting a vivid picture of how alien worlds can defy our expectations of habitation and warmth. HD 189733b is a fascinating exoplanet that challenges our understanding of what constitutes a habitable environment. This large, gaseous planet orbits a star much like our Sun, but conditions there are extreme. Imagine a world constantly battered by fierce winds exceeding the speed of sound, with temperatures soaring to unbearable levels. The atmosphere is thick and composed of gases that would be toxic to human life, including clouds rich in glass-like particles that rain sideways due to the relentless storms. These harsh conditions may seem like an outright dismissal of life as we know it. However, life on Earth has shown incredible resilience, thriving in environments once thought to be inhospitable. Microbial life has been discovered in the deepest ocean trenches and the most acidic lakes. In that regard, it's essential to broaden our definition of life. The advanced technology that has allowed scientists to detect exoplanets hints that there may be forms of life adapted to extreme environments elsewhere in the universe. This adaptation can manifest in biochemical processes unlike those we are familiar with. For example, organisms could potentially utilize chemical reactions that are fundamentally different from the carbon-based life forms we know, perhaps even using alternative elements. Despite the extremely harsh atmosphere of HD 189733b, the possibility that life in some form could exist there cannot be entirely ruled out. Still, as we stand today, any discussion about life on this planet is highly speculative. Understanding the limits of life on Earth and the extreme conditions it can endure will be crucial in guiding future explorations beyond our solar system. Gliese 581 Days is a fascinating exoplanet that stirs both enthusiasm and caution among scientists. Orbiting a star known as a red dwarf, this planet is located within the so-called habitable zone, where conditions might be just right for liquid water to exist. The prospect of water is crucial because it increases the chances of finding life similar to that on Earth. This proximity to the habitable zone makes Gliese 581 Days an exciting target for future research, as the mere possibility of life fuels our curiosity about what kinds of organisms might thrive in alien environments. However, the excitement doesn't come without its share of unsettling considerations. Gliese 581 Days' atmosphere could be vastly different from our own. Its surface conditions might be extreme, with pressures and temperatures that could challenge the survival of many known life forms. If the planet's atmosphere is thick and rich in greenhouse gases, it could generate extreme surface temperatures and weather phenomena that we struggle to fully understand. Moreover, the gravitational influence of a nearby star system can lead to unpredictable tidal forces that might significantly affect the planet's structure and climate. This unpredictability raises the stakes for exploration. The survey of its atmosphere alone might reveal a range of gases that hint at biological processes or, conversely, suggest a toxic environment inhospitable to life. Gliese 581 Days stands out as a double-edged sword in the quest for alien life. Its position in the habitable zone and potential for liquid water present thrilling prospects for discovery, while the unknowns about its environment instill a sense of trepidation. This blend of excitement and caution is what makes Gliese 581 Days a captivating subject for future exploration as we seek to unravel the mysteries of our universe and the possibilities it holds. Gliese 581 Days occupies an intriguing position within its star's habitable zone, often described as the region around a star where conditions may be just right for liquid water to exist on a planet's surface. This zone is critically important because water is considered a fundamental ingredient for life as we know it. Imagine this zone as a delicately balanced area, not too close to the star where temperatures are scorching, and not too far, where it's frigid. As Gliese 581 Days orbits its host star, it receives enough energy to potentially maintain liquid water on its surface, thus creating an environment where life could emerge. However, there are several factors that come into play beyond just being within this zone. The planet's surface characteristics, like its atmosphere, temperature stability, and any geological activity, also play significant roles. A thick atmosphere could help regulate temperature and protect against harmful cosmic radiation, while varied terrain could create different ecological niches. Furthermore, Gliese 581 Days is classified as a super-Earth, meaning it is larger than Earth, which gives it a different gravitational pull. This might influence atmospheric retention, affecting how well it can support the conditions necessary for life. The unique conditions of its atmosphere and potential geological makeup could create a range of environments, adding complexity to the prospects for biological processes. While its location is promising, it is just one piece of the puzzle in understanding Gliese 581 Days' potential for hosting life. Researchers continue to study this planet and others like it to better grasp the myriad conditions that could foster life beyond our own world. Gliese 581 Days, an exoplanet located in the habitable zone of its star, presents a fascinating array of potential weather patterns that could be described as extreme. Its unique atmospheric conditions stem largely from its position and the type of star it orbits. As a planet that is larger than Earth, it likely has a robust atmosphere, which could lead to significant weather phenomena. The planet may experience winds of astonishing strength, driven by temperature differences between its day and night sides. Since Gliese 581 days is tidally locked, it shows one face to its star permanently. This creates a dramatic contrast, one side bathed in continuous light and the other cloaked in perpetual darkness. Such a setup can lead to intense thermal gradients, with scorching temperatures on the sunlit side and freezing cold on the dark side. This temperature disparity could spawn fierce storms, with winds rushing from the illuminated side to the dark side in an attempt to equalize those temperatures. Additionally, if Gliese 581 days has a composition that includes water, it could witness turbulent weather with the formation of clouds and precipitation. The constant heating on one side could lead to boiling oceans, while on the dark side, condensation might occur, resulting in sudden downpours or even massive storms. The presence of thick clouds could perpetuate cycles of rain and drought, dramatically impacting any potential biosphere. Furthermore, extreme weather systems could develop due to the interactions between surface temperatures and the atmosphere. If enough water vapor were present, the planet could experience violent lightning storms, where high levels of electrical activity discharge due to the intense heat accumulating in the atmosphere. All these factors contribute to a picture of Gliese 581 days as an ominous world with weather patterns that could be as tumultuous and unpredictable as they are fascinating. The combination of extreme temperature variations, the potential for storms, and the peculiarity of its day-night cycle paints a vivid portrait of a planet that is both captivating and foreboding. Red dwarf stars, like the one at the center of the Gliese 581 system, are essential players in shaping the environment of their orbiting planets. These stars are smaller and cooler than our Sun, which significantly impacts the conditions on nearby worlds such as Gliese 581 days. With a lower luminosity, a red dwarf emits far less light and heat, meaning that habitable zones, regions where conditions might be right for liquid water, are much closer than they are in solar systems with larger stars. On Gliese 581 days, this proximity to the red dwarf can lead to a unique environment. The planet is likely tidally locked, meaning one side constantly faces the star while the other remains in perpetual darkness. This could create stark temperature variations. The sunlit side might be warm and potentially habitable, while the dark side could be frigid and inhospitable. The potential for atmospheric circulation might help regulate these temperatures, allowing heat and moisture to transfer from the daylight side to the night side, possibly enabling conditions suitable for life across the planet. Additionally, red dwarfs have long lifespans, often lasting tens of billions of years. This stability could provide a lasting environment for Gliese 581 days, giving it ample time to develop and sustain any potential life forms. However, the star's activity presents another layer of complexity. Red dwarfs are known for their stellar flares, which can emit bursts of radiation that might strip away the atmosphere of a nearby planet or affect the chemistry of its surface. The characteristics of a red dwarf star nurture a potential paradise on Gliese 581 days, while also presenting challenges. The closeness to the star, the likelihood of tidal locking, long-term stability, and the effects of stellar activity all intertwine to create a complex and fascinating picture of life-sustaining possibilities against a backdrop of cosmic forces. WASP-12b presents an extreme atmosphere, characterized by a composition that poses serious challenges for potential life forms. This exoplanet orbits so close to its host star that its surface temperature reaches staggering extremes, likely exceeding temperatures found in any environment on Earth. This intense heat results in thick layers of vaporized materials, creating a harsh, unyielding atmosphere. One of the most menacing features of WASP-12b's atmosphere is the presence of heavy metals and other chemical compounds. Elements such as titanium and iron are believed to exist in gaseous forms due to the planet's relentless heat. These metals, usually solid or liquid at Earth-like temperatures, become harmful gases at the temperatures prevalent on WASP-12b, resulting in a highly toxic environment. Additionally, the atmosphere likely contains significant amounts of hydrogen, contributing to a crushing pressure that adds to the planet's inhospitable conditions. The extreme proximity of WASP-12b to its star means it experiences intense radiation and tidal forces that not only heat its atmosphere but may also strip away lighter gases over time, contributing even more to its hostile nature. The overall composition and conditions of WASP-12b foster an environment devoid of the stable, life-sustaining features found on Earth, making it a prime example of a planet where survival in any familiar sense appears virtually impossible. The unique combination of high temperatures, toxic gases, and heavy atmospheric pressures marks WASP-12b as a threatening world far removed from our own. WASP-12b resides exceptionally close to its parent star in a relationship that creates one of the most extreme environments known. Imagine a planet orbiting so close to its star that it completes a full rotation in less than a day. The intense heat from the star turns the atmosphere of WASP-12b into a shimmering, tumultuous sea of gas. This constant barrage of radiation causes its atmosphere to expand dramatically and push outward, creating a unique phenomenon where the planet is literally being stripped away by stellar winds. The temperature on WASP-12b soars to such extreme levels that its atmosphere is likely made up of elements such as hydrogen and helium in a state far more energetic than we experience on Earth. These conditions also promote the presence of heavy metals like iron and titanium in the atmosphere, which can exist in gaseous form. This is far removed from the cooler, more stable climates we associate with our own planet. Furthermore, the relentless gravitational pull from the star leads to tidal forces that distort the shape of the planet itself, creating an oblong figure instead of a perfect sphere. This distortion allows the star to create incredibly large tides in the atmosphere, resulting in winds that can be supersonic, meaning they travel faster than the speed of sound. This volatile environment sets the stage for tremendous weather patterns, including fierce storms that rage continuously. WASP-12b epitomizes a world where the closeness to its star transforms it into a place of extreme temperatures, constant atmospheric upheaval, and a strikingly hostile environment that challenges our understanding of planetary formation and survival. WASP-12b stands out in the cosmos, not only because of its unique attributes, but also due to its extreme conditions, which contribute to its reputation as a scary planet. This exoplanet orbits very close to its parent star, resulting in a surface temperature that is extraordinarily high. Imagine temperatures scorching enough to vaporize common materials. Indeed, anything in its atmosphere gets heated to the point of being in a gaseous state. This intense heat creates a violent environment that is inhospitable to any form of life as we know it. In addition to the extreme heat, WASP-12b is incredibly dense. This density arises not just from the materials that constitute its mass, but also from the tremendous gravitational forces it experiences due to its proximity to its star. Such intense gravity compresses the planet's atmosphere, creating pressures that would crush ordinary terrestrial objects. The combination of high temperature and density creates a thick, tumultuous atmosphere full of unusual chemical processes that can lead to phenomena such as intense storms or even strange weather patterns. Furthermore, this planet experiences what is known as tidal locking, which means one side is perpetually facing its star while the other remains in cold darkness. This adds to the dichotomy of extremes, where one half sizzles under relentless solar radiation and the other likely endures bitterly low temperatures, further underscoring its terrifying nature. All these factors, extreme heat, high density, and harsh atmospheric conditions, paint a picture of a planet that poses incredible challenges for any exploration efforts and challenges our understanding of what a planet can be, marking WASP-12b as a truly frightening example of the diversity of worlds beyond our own. WASP-12b is an exoplanet that captivates scientists and space enthusiasts alike, not just for its size and proximity to its parent star, but also for the unique way it reflects light. Picture a world where the atmosphere is an otherworldly mix of extremes, producing a surreal spectacle as light plays off its surface. This exoplanet is notorious for being one of the darkest known, with a shade that saps much of the light that hits it, almost resembling that of charcoal. The light that does get reflected offers intriguing insights into its atmospheric composition and structure. Unlike Earth, where we see blue skies due to scattering, WASP-12b's thick atmosphere absorbs more sunlight than it reflects. This distinct characteristic creates an aura of mystery, as it suggests an environment filled with complex clouds possibly made up of elements like sodium or other metals that exist in gas form due to the intense heat. The immense gravitational pull of WASP-12b causes it to be stretched into an oval shape, creating tidal forces that contribute to its high temperatures. As a result, this exoplanet orbits incredibly close to its parent star, leading to side effects as light interacts with its atmosphere in unusual ways. This combination of extreme conditions generates fascinating observations, such as rapid changes in brightness as the planet rotates. The shifting light display not only adds to its mysterious charm, but also challenges our understanding of atmospheric physics on such a distant world. Every glimpse of WASP-12b becomes a tantalizing puzzle, inviting researchers to explore how such a dark and dynamic atmosphere could hold secrets about planet formation, evolution, and the diverse possibilities of worlds beyond our own. TRES-2b has garnered attention as one of the darkest exoplanets ever discovered, and the reason behind this intriguing title lies in its extraordinary ability to absorb light. Imagine a surface that is devoid of any reflection. That's what TRES-2b exemplifies. Approximately 97% of the light that strikes its atmosphere is absorbed, leaving only a tiny fraction to be reflected back into space. This extreme darkness results from its unique composition and atmospheric conditions. The planet's atmosphere is thought to be rich in substances like vaporized sodium and potassium, which not only contribute to its absorbing properties but also add to its exotic nature. When light interacts with these elements, they do not reflect it but instead convert it into heat, making the planet appear incredibly dim compared to others. Furthermore, TRES-2b orbits very close to its host star, resulting in high temperatures that likely enhance these absorbing characteristics. The heat may lead to the dissipation of light as infrared radiation rather than visible light, which is why we may perceive it as an abyss in the cosmos. In a universe filled with vibrant, glowing celestial bodies, TRES-2b's nearly pitch-black exterior makes it stand out, presenting a mystery of light and darkness that beckons further exploration. TRES-2b is often described as one of the darkest exoplanets known, possessing a unique ability to absorb nearly all the light that hits it, about 97%. This incredible light-absorbing property creates a strikingly ominous presence in the vastness of space. Imagine gazing at a vast void where instead of reflecting the warmth of sunlight, this planet swallows it whole, making it appear almost invisible against the backdrop of the stars. The significance of this characteristic extends beyond mere aesthetics. It offers insights into the atmospheric composition and surface conditions of the planet. TRES-2b's atmosphere is thought to be rich in substances like sodium and potassium, which contribute to its deeply dark appearance. This darkness could indicate a dense, cloudy atmosphere that traps heat, making temperatures on the planet excessively high. The lack of reflected light adds to the mystery, raising questions about the processes that govern such extreme environments. Additionally, the light absorption hints at possible interactions with energy, impacting how the planet radiates heat and may influence its weather patterns. The dark surface could also enhance its thermal efficiency, leading to a hot, inhospitable world, one that starkly contrasts with the shimmering, bright planets we often envision. TRES-2b's foreboding nature echoes throughout the cosmos, reminding us that not all worlds are welcoming. Some are engulfed in shadow, adding depth to our understanding of planetary diversity in the universe. TRES-2b, known as one of the darkest exoplanets ever discovered, absorbs an astonishing amount of light. Imagine a celestial body coated in a reflective substance so minimal that it barely gleams. This extreme darkness means that less light heats the planet. As a consequence, the atmosphere of TRES-2b experiences unique conditions shaped by this limited energy absorption. The planet's surface, shrouded in shadows, contributes to exceedingly low temperatures. With such a minimal reflection of light, the heat that does accumulate does so unevenly, leading to potential atmospheric phenomena. This could result in unusual weather patterns, possibly featuring strong winds or even storms driven by the stark temperature differences in various regions. Exploring TRES-2b presents significant challenges. The lack of brightness makes it difficult for space telescopes to detect it, as they rely on light to capture images or gather data. Moreover, the atmospheric conditions, potentially laden with exotic chemicals, might be inhospitable for instruments designed for more familiar environments found within our solar system. However, the study of TRES 2b remains intriguing. Its extreme darkness may offer insights into atmospheric science, especially regarding how atmospheres can evolve in such peculiar environments. Understanding these elements could pave the way for discoveries about similar exoplanets, ultimately revealing more about the diverse tapestry of worlds scattered throughout the universe. TRES 2b, a planet located outside our solar system, is known for its exceptionally dark atmosphere, reflecting less than 1% of the light that hits it. This characteristic makes it one of the darkest known exoplanets, absorbing almost all incoming starlight, akin to how charcoal looks under direct sunlight. This striking absorbent nature raises intriguing questions about its composition and atmospheric dynamics. Scientific curiosity is further piqued by the extreme temperatures on TRES 2b. The planet orbits very close to its star, leading to scorching conditions that can reach levels hotter than a furnace. This intense heat causes bizarre atmospheric phenomena, including the potential for unusual weather patterns and chemical reactions that may produce strange compounds that are not found on Earth. Moreover, researchers have observed potential signs of strange, possibly luminous materials that might exist within TRES 2b's clouds. These substances could include vaporized minerals or even exotic chemicals playing a role in the planet's obscure and unique atmosphere. This interplay of light absorption, extreme temperatures, and potentially dynamic weather systems presents a fascinating area for exploration. In exploring these eerie phenomena, scientists hope to unlock secrets about the processes shaping alien worlds, broadening our understanding of planet formation and the diverse environments that can exist in the cosmos. The mysteries of TRES 2b demonstrate how much there is to learn about the universe beyond our own planet, igniting excitement and curiosity among astronomers and planetary scientists alike. The discovery of Proxima Centauri b, a planet orbiting the closest star to our solar system, has sparked significant interest in the possibility of life beyond Earth. It orbits within what is termed the habitable zone, where conditions could allow for liquid water, a vital ingredient for life, as scientists have come to understand it. However, this distant exoplanet presents a paradox. While it resides in this seemingly favorable zone, Proxima Centauri b faces constant bombardment from its host star's powerful radiation and stellar flares. This intense radiation can strip away a planet's atmosphere over time, creating a hostile environment. Even with its prime location for temperature regulation, the atmospheric conditions necessary for sustaining life as we know it may be severely compromised. This situation challenges our traditional views of habitability. For years, we have assumed that the presence of liquid water and a suitable distance from a star would guarantee a planet's ability to support life. Yet, Proxima Centauri b illustrates that other factors, such as a planet's atmosphere and magnetic field, are critical for sustaining any potential forms of life. Thus, the study of Proxima Centauri b invites scientists to rethink what we consider habitable. It pushes us to explore a broader range of possibilities, suggesting that sometimes even planets in the Goldilocks zone might be far from hospitable. The lessons learned from Proxima Centauri b encourage further investigations into exoplanets, emphasizing the need for a more nuanced understanding of what it truly means for a world to support life. Proxima Centauri b orbits a red dwarf star known for its unique characteristics, which create an environment that poses significant challenges for the potential for life. First, let's consider the star itself. Red dwarfs are much cooler and less luminous than our Sun, meaning Proxima Centauri b falls within a zone where liquid water could exist, referred to as the habitable zone. However, this proximity to its star comes with consequences. The planet is likely tidally locked, a condition where one side consistently faces the star while the other remains in perpetual darkness. This can create extreme temperature differences between the two sides, leading to harsh climates that might not be conducive to life as we know it. The day side could be scorched by intense radiation, while the night side may plunge into frigid conditions. Additionally, Proxima Centauri is active, experiencing frequent solar flares that can release bursts of radiation detrimental to life. These flares could strip away the atmosphere of an orbiting planet, resulting in a hostile environment lacking essential elements for sustaining life, such as water. Also, the planet's atmosphere would need to be substantial enough to provide protection from this intense radiation and to stabilize temperatures. If it exists, this atmosphere must face the constant challenge of being eroded by the powerful stellar activity. While Proxima Centauri b lies within a habitable zone, the combination of its star's characteristics, its potential tidal locking, and the risks from high radiation make the conditions on this exoplanet tough for supporting life. Each of these factors creates an environment that may not readily allow for the complex interactions we associate with thriving ecosystems on Earth. Tidal locking is a fascinating phenomenon that occurs when the gravitational forces between two celestial bodies cause one to rotate on its axis in such a way that it always shows the same face to the other. In the case of Proxima Centauri b, which orbits the closest star to our solar system, this means that one side of the planet is perpetually bathed in sunlight, while the other remains in perpetual darkness. This lack of rotation might create extreme conditions, as the side facing the star would experience constant daylight and high temperatures, while the dark side could become extremely cold, leading to challenging climates that could hinder the development of life as we know it. Over time, this could result in a stark contrast in environments, lush and heated on one side, possibly barren and freezing on the other. Additionally, the atmosphere plays a crucial role in habitability. If Proxima Centauri b has a thin atmosphere, the heat might not distribute evenly across the planet. This could lead to intense storms or winds, as air attempts to move from the hot side to the cold. Conversely, if it has a thick atmosphere, it might help to moderate temperatures, yet it could also become a runaway greenhouse, similar to Venus, if conditions aren't just right. Then there's the aspect of stellar radiation. Proxima Centauri is known for its flare activity, powerful bursts of radiation that can strip away atmospheres or irradiate the surface of a planet. A planet in tidal lock might not be able to escape this constant bombardment effectively, further complicating its chances for hosting life. These factors combine to create a complex and potentially hostile environment on Proxima Centauri b, raising serious questions about its ability to support life. The concept of a world forever caught in a gravitational embrace with its sun poses difficulties that make the prospect of habitability both intriguing and ominous. Scientists view solar flares as powerful bursts of energy that can greatly impact Earth and its technological infrastructure. These flares occur when the sun's magnetic fields become temporarily tangled and release vast amounts of energy, often accompanied by coronal mass ejections, large clouds of solar particles that can be hurled into space. When a solar flare erupts, it emits radiation across different wavelengths, including ultraviolet and X-rays. This energy travels through space at the speed of light, meaning it reaches Earth in just over 8 minutes. While we cannot physically feel this radiation, its effects can be significant. For example, solar flares can disrupt radio signals and satellite communications, leading to momentary blackouts or navigational errors for aircraft and ships. Scientists are particularly cautious of larger flares, as these can produce electromagnetic bursts that have the potential to affect power grids on Earth. In extreme cases, such severe solar activity could lead to widespread electrical outages, necessitating careful monitoring and prompt responses from utility companies. To gauge the threat of solar flares, researchers rely on a variety of instruments stationed in space, such as satellites equipped to observe sunspots and track solar activity in real time. By studying the sun's behavior and identifying patterns associated with increased solar flare activity, scientists can provide early warnings and equip society to face potential disruptions resulting from these solar phenomena. The goal is not just to understand the sun's activity, but to mitigate its impact on our increasingly digital world. Under the thick, steamy atmosphere of the exoplanet GJ 1214b, a world located in the constellation of Ophiuchus, we might encounter several fascinating yet terrifying phenomena. This planet is classified as a mini-Neptune, with a hazy atmosphere that is rich in water vapor and potentially other gases, creating an environment unlike anything found on Earth. The surface pressure on GJ 1214b could be significantly higher than what we experience here. Imagine a place where the crushing weight of the atmosphere surrounds you, making every breath an immense challenge. The high temperatures, bolstered by the dense atmosphere, may lead to an oppressive greenhouse effect, with sweltering conditions that drive temperatures to extreme levels. Considering the composition of the atmosphere, there are strong possibilities of acid clouds forming, which could contain corrosive elements. This would make the idea of existing life very different, if it exists at all. Instead of familiar life forms, we might find bizarre organisms adapted to such extreme conditions, capable of thriving in acidic environments or even drawing energy from the planet's atmospheric chemistry in ways we've yet to comprehend. Moreover, GJ 1214b might experience high-speed winds driven by the intense heat and pressure differences within its atmosphere. These winds could lead to violent storms that rage across the landscape, similar to those seen on gas giants. Thick clouds may shield the planet from our view, but beneath there could be turmoil, with lightning illuminating the chaotic darkness in flashes of fury. Additionally, the interaction of the powerful atmosphere with magnetic fields generated by the planet itself could create electrifying phenomena. Imagine dazzling atmospheric displays akin to auroras on Earth, but on a scale far larger and more dramatic, casting eerie glows across an alien landscape. The depths of this thick atmosphere could hold even more mysteries, such as enormous oceanic bodies of superheated water, where water vapor and liquid water might coexist. If such bodies exist, they could be teeming with unknown chemical reactions, creating a turbulent environment that challenges the very definition of life as we know it. GJ 1214b could be a realm of awe and terror, a world shrouded in steam and pressure, where life, if present, would defy our expectations, and where every aspect of its environment pushes the boundaries of what is possible. GJ 1214b, an intriguing exoplanet located approximately 44 light-years from Earth, has captured scientists' imaginations with its potential to host a vast ocean, often referred to as a water world. This possibility is tied to its unique composition and characteristics. GJ 1214b is classified as a super-Earth, meaning it is larger than our planet but still rocky. However, its atmosphere likely includes significant amounts of hydrogen and helium, creating conditions conducive to trapping heat. The temperature on GJ 1214b is relatively mild by extraterrestrial standards, which raises the likelihood that water could exist in a liquid state across vast regions of its surface. If the planet has a thick layer of water beneath its atmosphere, it may be several kilometers deep, forming a continuous ocean that envelops the planet. This scenario opens exciting questions about the potential for life and the planet's geology. However, such a water world concept is daunting for several reasons. First, the high pressure under the mass of water could lead to extreme conditions that make it difficult for any life forms we are familiar with to survive. The immense depths may create environments that are both dark and hostile, devoid of light and nutrients. Furthermore, with the potential absence of land, environmental processes crucial for life's development, such as those that occur on terrestrial planets, could be significantly diminished. The planet's atmosphere may also pose challenges. If it contains thick clouds of vapor, it could inhibit our ability to observe surface features or determine what lies below. Understanding GJ 1214b requires grappling with the complexities of fluid dynamics, chemical conditions, and the vast unknowns of potential ecosystems. Thus, while the concept of a water world is captivating, the realities of such an environment highlight the difficulties scientists face in studying and understanding distant planets. GJ 1214b, an exoplanet orbiting a distant star, is often described as a place of extremes, and its high atmospheric pressure significantly contributes to this reputation. Imagine the crushing force of deep ocean water, where every inch downward feels heavier due to the mass of water above. On GJ 1214b, this sensation is magnified immensely. The planet's atmosphere is thick, leading to pressures much higher than those experienced on Earth. This high pressure can cause significant changes in the composition and states of matter. One of the primary concerns with high atmospheric pressure is its potential to create an environment unsuitable for life as we know it. Unlike the relatively gentle conditions on Earth, the extreme pressure on GJ 1214b might turn water into a dense fluid rather than a gas or liquid as we typically encounter. This could lead to the formation of exotic forms of matter or chemical reactions that wouldn't occur under normal conditions, marking the planet as a hostile environment. Additionally, the intense pressure could affect how temperatures behave. On GJ 1214b, warm temperatures combine with high pressure to create a unique thermal environment that might prevent heat from escaping efficiently. This could result in uniformly high temperatures that make surface conditions even more daunting. The combination of heat and pressure can lead to dynamic weather patterns, possibly violent storms or unrelenting heat, shrouding the planet in a constantly moving atmosphere. These characteristics culminate in a world that feels both alien and formidable. GJ 1214b is not just another planet. It embodies an extreme environment where common elements behave in unpredictable ways, leaving scientists and enthusiasts captivated by its daunting allure. The exoplanet GJ 1214b presents an intriguing but daunting mystery for researchers, primarily due to the hostile and unknown elements of its environment. Discovered orbiting a red dwarf star, this planet resides in a region where conditions can be starkly different from those on Earth. Scientists suspect it might have a thick atmosphere, possibly rich in water vapor, yet the exact composition remains uncertain. The possibility of extreme pressures and temperatures raises concerns about the planet's ability to support any known forms of life. One of the most disconcerting aspects is the planet's potential atmosphere, which could contain harmful substances or be so dense that it prevents any meaningful exploration. The unknown physical interactions between this atmosphere and the planet's geological features make it difficult to predict what researchers might encounter. The atmospheric pressure, perhaps greater than that found in the deepest parts of Earth's oceans, poses a serious challenge to our fundamental understandings of habitability. Additionally, GJ 1214b's proximity to its star affects its environmental conditions dramatically. The intense radiation from its host star can lead to atmospheric erosion over time, altering the planet's landscape, and could even strip away essential elements required for sustaining life. This unpredictability invokes a sense of fear because it highlights the vast gap in our knowledge about environments so different from our own. The more researchers learn about GJ 1214b, the more they uncover its potential to defy expectations, which both fascinates and unsettles those who seek to understand the universe's myriad possibilities. Coro 7b is a fascinating exoplanet located incredibly close to its star, exposing it to intense heat that renders its surface nearly uninhabitable. Imagine a world where temperatures soar to a point that metal melts and vast oceans of molten rock spread across the landscape. The relentless sunlight creates a constant glare that not only scorches the surface but also prevents any form of cooling. On Coro 7b, one side is perpetually bathed in light, while the opposite side is shrouded in darkness. This drastic temperature difference leads to extreme weather patterns, where the side facing the star experiences temperatures so high that vaporized rock might billow into the atmosphere, while the cooler side could be marked by plummeting temperatures. The atmosphere itself, if it exists, is likely choked with toxic gases and heavy clouds made from elements that would seem familiar to a volcanic environment on Earth. In such extreme conditions, the landscape is dominated by tectonic activity. The heat generates enormous geological forces, causing violent eruptions and reshaping the planet's crust. This results in a hellish terrain filled with volcanic plains, towering mountains formed from hardened lava, and rivers of molten material snaking their paths along the hot surface. Overall, Coro 7b stands as a vivid example of how proximity to a star can produce a landscape that pushes the limits of what we define as habitable. It serves as a stark reminder of the diverse worlds that exist beyond our solar system, each with their own unique and extreme characteristics. The surface of Coro 7b is an extraordinary sight, but it poses significant challenges for habitability. This exoplanet, located outside our solar system, is categorized as a rocky planet, similar to Earth, yet its environment diverges drastically from what we consider livable. One of the most striking aspects of Coro 7b is its proximity to its host star, leading to extreme temperatures. The side facing the star experiences blistering heat, while the opposite side remains perpetually cold. This drastic thermal difference creates a landscape that is in constant turmoil, with the high temperatures making it impossible for water to exist in its liquid form. Instead, any water present would likely vaporize, blanketing the surface with clouds of hot gas. Furthermore, the intense radiation from the nearby star contributes to a harsh atmosphere, stripping away any potential for a stable biosphere. In addition to extreme heat, the constant volcanic activity documented on its surface adds another layer of danger. Eruptions can spew molten rock and gases into the atmosphere, contributing to an ever-shifting, hostile environment. The combined effects of extreme temperatures, harsh radiation, and volcanic activity create a world that is not only uninhabitable, but also a stark reminder of the diversity of conditions that can exist in the universe. Without the necessary conditions for life as we know it, like stable temperatures, liquid water, and a protective atmosphere, Korot 7b remains a world that is both fascinating and foreboding. Korot 7b is an exoplanet that has captured the imagination of scientists and enthusiasts alike due to its extraordinary volcanic activities. Imagine a world where molten rock and sulfuric gases spew from the surface. That's the reality of Korot 7b as described by astronomers. This planet is classified as a rocky world, much like Earth, but its environment is starkly different. Positioned so close to its star, Korot 7b experiences extreme temperatures that can cook the surface. This intense heat causes the planet's surface material to melt, leading to current volcanic eruptions. Picture a landscape riddled with bubbling lava lakes and thick clouds of gas. This gives Korot 7b its fearsome reputation, intensifying the sense of danger associated with it. These persistent volcanic activities contribute not only to the planet's hostile atmosphere, but also play a critical role in its long-term geological evolution. The constant release of material can lead to the creation of new landforms and influence the chemistry of the atmosphere. Moreover, the searing conditions mean that any potential for life, as we understand it, is virtually non-existent here. As scientists continue to study Korot 7b, its volcanic eruptions serve as a vivid example of how varied and dynamic planetary processes can be beyond our own solar system. This unique combination of high volcanic activity and extreme temperatures indeed shapes its reputation as one of the most fearsome worlds known to orbit a distant star. Korot 7b, a rocky exoplanet located about 600 light-years away, orbits its star in a remarkably short period, taking just a little over 20 hours to complete one full revolution. This rapid orbital period has profound implications for the planet's environmental conditions. Being so close to its host star, Korot 7b experiences intense solar radiation and extreme surface temperatures that can be far hotter than anything found on Earth. The side facing the star is subjected to relentless heat, while the opposite side remains in perpetual darkness. This results in a stark temperature difference between the two halves, leading to dynamic atmospheric conditions. The extreme heat on the starward side can cause various compounds, like molten rock or even metals, to exist in liquid form, creating a landscape that is incredibly hostile. On the night side, temperatures can drop dramatically, possibly allowing for the condensation of certain gases into clouds or even frost, depending on the atmospheric composition. Moreover, the tidal forces exerted by the star likely keep the planet in a synchronous rotation, meaning one side perpetually faces the star. This lock can create extreme weather patterns, with constant winds trying to balance the dramatic temperature differences. Such conditions make it a prime example of how orbital mechanics profoundly influence planetary climates and compositions. Understanding Korot 7b provides valuable insights into the conditions that can exist on exoplanets, especially those orbiting close to their stars, and the extremes of environments that can emerge in versatile planetary systems. Kepler-22b is a tantalizing exoplanet that resides in the habitable zone of its star, a region where conditions could permit liquid water. However, several eerie characteristics complicate its potential to support life. First, the planet's size is crucial. It is larger than Earth, suggesting that it might have a thick atmosphere and high surface pressures. These factors could create extreme weather patterns, including intense storms that make the environment hazardous. Moreover, the star it orbits is a type that behaves differently than our Sun. It is cooler and emits less radiation, which could affect the atmospheric composition of Kepler-22b. a thick atmosphere could trap heat, potentially leading to a greenhouse effect that might make the environment too hostile, with scorching temperatures at the surface. Additionally, the potential for Kepler-22b to harbor a liquid ocean raises other concerns. Such vast bodies of water could lead to a complex interplay of chemistry and physics. While this environment could theoretically support some form of life, it might also create conditions that are very different from those on Earth, possibly harboring toxic substances that could be harmful. The uncertainty surrounding its gravity is another factor. With its larger size, Kepler-22b could exert a gravitational pull that is significantly stronger than Earth's. This could impact how any atmosphere evolves, as well as the types and forms of life that might be able to survive there. The gravitational influence might also lead to geological activity, like volcanic eruptions, that would create further environmental hazards. Taken together, these characteristics make Kepler-22b a planet of dual nature. It tantalizes with the possibility of life while simultaneously presenting a range of inhospitable conditions that may blur the lines between a habitable world and one that is perilous. In the vastness of space, where life's possibilities are as remarkable as they are unpredictable, Kepler-22b stands out as a prime subject for exploration and curiosity, a constant reminder of how much remains to be understood about our universe. Kepler-22b is classified as a potentially habitable exoplanet due to its location in a star's habitable zone, where conditions could allow for liquid water. However, despite these Earth-like qualities, its environment may differ significantly from our own. One of the main factors is its size. Kepler-22b is approximately 2.5 times larger than Earth, which suggests it has a stronger gravitational pull. This could result in a thicker atmosphere, with higher pressure that may retain gases like carbon dioxide and methane, creating a greenhouse effect that could warm the surface significantly. Such an atmosphere might change how water behaves, potentially leading to surface oceans, but also to extreme weather patterns, unlike anything we experience here. The star Kepler-22b orbits is a slightly cooler, more stable type than our Sun. This means that the planet receives less energy overall, which could affect temperature distributions. While Earth experiences seasons due to tilt and rotation, Kepler-22b's climate might behave quite differently, possibly relying on factors like its orbit's eccentricity and rotation period. If it has a slow rotation, one side may experience continuous daylight, while the other faces perpetual darkness, creating drastic temperature differences that could lead to harsh living conditions. Additionally, the geological makeup of Kepler-22b remains unknown. It might possess a rocky surface like Earth's, or it could be primarily composed of ocean, ice, or even gaseous layers. Such variations would influence the potential for life forms, ecosystems, and even the availability of essential minerals. Moreover, if life exists there, it could have evolved under vastly different circumstances. Adaptations in organism structure, metabolism, and methods of energy acquisition might be tailored to an environment rich in other atmospheric gases or influenced by different solar radiation levels. While Kepler-22b shares some characteristics with Earth, its size, atmosphere, distance from its star, and potential geological features might create a landscape that is drastically different, contributing to a unique environmental canvas that shapes its climate and potential life. Kepler-22b, a planet located in the habitable zone of its star, has drawn significant interest, particularly concerning its atmosphere and potential for life. Theories about its atmosphere vary widely, leading to a sense of mystery and even unease. Some scientists speculate that this exoplanet could possess a thick, dense atmosphere similar to that of Venus, where unbearable temperatures and crushing pressure would make survival impossible. The idea of a greenhouse effect running wild raises fears about extreme weather conditions and toxic environments that could render the surface a hostile realm. Another haunting theory suggests that Kepler-22b may harbor clouds of liquid water or even ammonia, creating an unsettling scenario where life might struggle against an environment of perpetual storms and chemical hazards. This imagined atmosphere might not only facilitate the survival of bizarre microorganisms, but could also prevent any familiar forms of life from evolving. Some researchers also entertain the possibility of an atmosphere rich in methane or other gases that, on Earth, are associated with decay or the absence of life. This presents a chilling thought. What if Kepler-22b's atmosphere holds mysterious biochemistry entirely alien to us, suggesting either a world devoid of life or a realm filled with unknown forms of existence, fundamentally different from what we understand? The combination of these speculative theories creates an atmosphere of tension and intrigue around Kepler-22b. The planet stands as both a beacon of hope for discovering extraterrestrial life and a reminder of the potential dangers that come with exploring the universe's many enigmas. Each theory raises questions about habitability, life's resilience, and the extremes that nature can take, leaving us pondering what truly lies beneath the thick clouds of Kepler-22b. The discovery of Kepler-22b marked a significant moment in our exploration of potentially habitable worlds beyond our solar system. Previously, the concept of the Goldilocks zone referred to the region around a star where conditions might be just right, neither too hot nor too cold, for liquid water to exist on a planet's surface. Kepler-22b, orbiting a star similar to our own, resides comfortably within this zone. However, its discovery prompts us to rethink the parameters of this idea. Firstly, Kepler-22b is not merely an Earth-like planet but a larger world, classified as a super-Earth. Its size and composition suggest that it could have a thick atmosphere and various climates, potentially leading to diverse habitats. This challenges our prior assumptions that only Earth-sized planets are suitable for life. The new understanding encourages scientists to consider a broader range of planetary characteristics that may support life. Additionally, the findings from Kepler-22b demonstrate that the Goldilocks zone isn't a strict boundary, but a dynamic range influenced by other factors such as atmospheric pressure, composition, and stellar radiation. For instance, a planet with a dense atmosphere might retain heat better, allowing it to support liquid water even if it orbits closer to the inner edge of this zone. Consequently, this discovery opens the door to exploring a variety of planetary conditions leading to habitability. Kepler-22b reshapes our understanding of habitable zones by illustrating that the criteria for sustaining life are more nuanced than merely being in the right position relative to a star. It encourages astronomers to explore diverse planetary systems further and consider the myriad ways life might adapt in varying environments across the universe. The Great Red Spot on Jupiter is an extraordinary and colossal storm that has raged for centuries, making it one of the most formidable weather phenomena in our solar system. It is a massive anticyclonic storm, meaning it rotates in the opposite direction to cyclonic storms found on Earth, and its size is truly astounding. It could easily encompass multiple planets the size of Earth within its swirling clouds. This storm is driven by Jupiter's unique atmospheric conditions, which include its rapid rotation and thick gaseous makeup. The planet spins on its axis much faster than Earth, completing a rotation in less than 10 hours. This swift movement generates powerful winds, which combined with the vast amounts of heat emitted from the planet's interior, foster an environment ripe for storm formation. The Great Red Spot is sustained by this continuous supply of energy and the prevailing wind patterns of Jupiter's atmosphere. The storm's striking reddish hue is attributed to complex chemical reactions within its clouds, possibly involving compounds like phosphorus and sulfur. These reactions contribute to the colorful and dynamic appearance that catches the eye of both astronomers and casual observers. Furthermore, what sets the Great Red Spot apart from Earth's storms is not just its size, but its longevity. It has been observed for over 300 years, showcasing its resilience and power. Continuous data from space missions reveal that while it may fluctuate in size and intensity, the storm has remained a constant feature of Jupiter's atmosphere, presenting a captivating subject for scientists seeking to understand weather phenomena far beyond our planet. The Great Red Spot serves as a testament to the complexity and scale of Jupiter's weather, representing an interplay of forces that creates one of the solar system's most formidable and enduring weather systems. Jupiter is renowned for its immense and tumultuous storms, which play a significant role in shaping its fierce and intimidating persona. At its core, Jupiter is a gas giant, primarily composed of hydrogen and helium, and its lack of a well-defined surface means that storms can grow and evolve without the constraints found on rocky planets. One of the most famous features is the Great Red Spot, a gigantic storm larger than Earth that has been raging for hundreds of years. This storm serves as a vivid display of Jupiter's turbulent atmosphere, fueled by the planet's rapid rotation and deep convective currents that draw heat from its interior. This heat drives powerful winds that can exceed incredibly high speeds, creating a chaotic weather system characterized by swirling clouds and fierce lightning. Jupiter's storms are not merely aesthetic phenomena, they embody the planet's dynamic nature. The storms operate in layers, with winds at various altitudes flowing in different directions, contributing to complex interactions that result in unpredictable weather patterns. These include the formation of dark cloud bands and white ammonia clouds, which create a striking visual contrast and a captivating display of nature's power. Moreover, their sheer scale and intensity highlight Jupiter's role as a planetary giant in our solar system. The storms act as a reminder of the violent forces at play, where turbulence can reshape the atmosphere in real time. This chaotic energy feeds into Jupiter's identity, illustrating a world where violent storms are not anomalies, but rather the norm. It's a planet where the beauty of its clouds is matched only by the peril inherent in its swirling depths, making Jupiter both mesmerizing and formidable. Jupiter's magnetic field is a formidable force, creating an environment that is far from welcoming for spacecraft. To understand this, envision Jupiter as a giant magnetic dynamo. Its intense magnetic field, far stronger than Earth's, extends millions of kilometers into space and creates a vast bubble known as the magnetosphere. This bubble traps charged particles from the solar wind and from the planet itself. As spacecraft approach Jupiter, they enter this magnetosphere, where they encounter a chaotic mix of radiation and high-energy particles. These particles can be incredibly harmful. Think of them as tiny but destructive missiles that target spacecraft. The radiation belts surrounding Jupiter contain particles that are millions of times more energetic than those found in Earth's radiation belts. This poses serious risks to both electronic systems and the health of any potential astronauts. Moreover, the region around Jupiter is extremely dynamic. Chaotic magnetic fluctuations can produce powerful bursts of radiation, which spacecraft must navigate carefully. Such an environment can lead to malfunctions in onboard instruments and systems, making it challenging to collect data and conduct experiments. In sum, while Jupiter's magnetic field offers many scientific opportunities for exploration, it simultaneously creates a treacherous battleground where every mission must be meticulously planned to withstand the powerful forces at play. Jupiter stands as the largest planet in our solar system, and its sheer size evokes both fascination and a sense of trepidation. Imagine a giant that could contain more than 1,000 Earths within its vast expanse. This colossal nature allows us to realize how small our own planet truly is in comparison. What makes Jupiter awe-inspiring is not simply its size, but also the grandeur of its swirling atmosphere, comprised of thick bands of clouds filled with storms that rage for hundreds of years. The Great Red Spot, a massive storm larger than Earth, is a tempest that has been continuously churning for centuries, and its scale highlights the dynamic and ever-changing nature of planetary weather systems. Observing such colossal features can ignite a sense of wonder about the complexities of our universe. On the other hand, the intimidating aspect lies in its unyielding environment, characterized by extreme pressures and temperatures that humans couldn't survive. The gravity on Jupiter is far stronger than that on Earth, meaning a person would feel incredibly heavy, making any movement laborious. Additionally, the planet releases more heat than it receives from the Sun, hinting at an active and turbulent interior with potentially violent storms. And there's the enormous magnetic field, which creates intense radiation rings around the planet that would pose a serious threat to any spacecraft approaching too closely. Overall, Jupiter's magnificence and danger serve as a reminder of the incredible forces at play in the universe, challenging our understanding of what is possible and highlighting our vulnerability in the vast, unfathomable cosmos. Uranus is unique among the planets in our solar system due to its extreme axial tilt. While most planets rotate with their axes somewhat upright, Uranus is tipped over so dramatically that it rotates on its side. This tilt is almost perpendicular to its orbit, leading to an extraordinary seasonal experience. As Uranus travels around the Sun, its significant tilt causes one hemisphere to receive sunlight continuously for about one entire quarter of its year, which is equivalent to over 2 decades of Earth time. When that part of the planet is in sunlight, it experiences constant daylight and warmer temperatures, resulting in a dramatic shift in its atmospheric conditions. Conversely, as the planet continues its orbit, that same hemisphere will then be plunged into a prolonged winter, where it remains in darkness for an equal stretch of time. This continuous cycle of sunlight and darkness creates extreme seasonal variations unlike anything seen on Earth. The bizarre occurrences on Uranus during these seasons arise from the intense atmospheric changes. With one hemisphere basking in sunlight, dynamic weather patterns emerge. Winds can become ferociously strong, with bursts of storms forming and dissipating under the influence of heat from the sun. When that hemisphere transitions into darkness, temperatures plummet, and the atmosphere can become quite still, leading to a period of relative calm, but also to eerie, long-lasting cold conditions. Moreover, the equinoxes, when the sun shines directly over the equator, cause abrupt shifts in the weather patterns as both hemispheres experience a transition. Atmospheric systems may buckle under the sudden change, resulting in chaotic storms. These seasonal extremes are essential for understanding not just Uranus's weather patterns, but also the complexities of planetary atmospheres in general. Each of Uranus's lengthy seasons reveals how the planet responds dramatically to the tilt of its axis, showcasing the intricate dance between its position and the sun. The surface of Uranus presents a captivating yet stark spectacle, mainly due to its icy, featureless appearance. Unlike other planets that display a variety of dynamic landscapes, Uranus's exterior is cloaked in thick clouds composed primarily of hydrogen and helium, along with methane, which gives the planet its striking blue color. The icy crust beneath these clouds mainly consists of water, ammonia, and methane ices, creating a smooth and uniform surface that lacks the mountains, valleys, or craters seen on more geologically active celestial bodies. This featureless surface contributes to a sensation of desolation, enhancing the chill of its environment. At frigid temperatures, Uranus is one of the coldest places in the solar system, with atmospheric temperatures plunging deep into the icy abyss. This coldness is accentuated by the planet's distance from the sun, leaving it dimly lit and deeply shrouded in mystery. The winds that whip through its atmosphere may stir up clouds but do not disturb the underlying ice, leading to an unsettling stillness across its surface. Moreover, the planet's unique tilt, one that positions it almost on its side, adds to the intrigue. This unusual orientation results in extreme seasonal variations and creates a sense of otherworldly eeriness, with potential weather patterns remaining hidden from view. The combination of its depthless blue hues, the uniform icy sheet, the extreme cold, and the tilted position makes Uranus a chilling spectacle full of beauty and isolation. Uranus is unlike any other planet in our solar system, and its magnetic and rotational characteristics add to its allure. To start with, Uranus's axis of rotation is tilted at a staggering angle, almost lying on its side compared to its orbital plane. This extreme tilt, which can be imagined as a bowling ball rolling almost flat, results in unique seasonal changes that last for years, creating a world where polar regions receive prolonged sunlight or darkness. The planet also has an unusual magnetic field that is markedly misaligned with its rotational axis. Imagine spinning a top. The magnetic field generated would normally align with the top's center of spin. However, Uranus defies this norm. Its magnetic field is tilted at an angle, creating a lopsided shape and an offset core. This means that the magnetic influence extends in unpredictable directions, resulting in fascinating auroras and electric currents within its atmosphere. These peculiarities foster intrigue among scientists and enthusiasts alike. The tilt of the planet leads to extreme weather patterns, such as intense storms with winds that can reach staggering speeds. The complex interactions between the planet's atmosphere and magnetic field can produce atmospheric phenomena that are truly one of a kind. Moreover, this unique combination of magnetic and rotational dynamics challenges our understanding of planetary formation and evolution. Why does Uranus have such an unusual tilt? How did its magnetic field develop? Each of these questions invites deeper exploration, keeping Uranus a captivating subject of study in the quest to unravel the mysteries of our cosmic neighborhood. Thus, Uranus stands as a testament to the bizarre and diverse characteristics of planetary systems, showcasing how one planet's rotation and magnetic behavior can prompt endless curiosity and scientific inquiry. The discovery of Uranus's faint rings enhances the planet's mysterious and somewhat eerie character. When we think of rings, we often picture the grand and colorful bands encircling Saturn. In contrast, Uranus's rings are far more subtle, consisting of narrow, dark bands that are difficult to see. This contrast plays into the planet's overall allure. Uranus, with its striking blue hue and unique tilt, already stands out in our solar system. It rotates on its side, giving it an irregular and unexpected rotation compared to most planets. The presence of these faint rings adds a layer of complexity to its enigmatic nature. Discovered in the early 1980s, these rings appear to be made up of small particles that range in size from tiny grains to larger boulders. Their elusive nature makes them feel otherworldly, as if they are part of some ghostly phenomenon in space. The rings also raise intriguing questions about their origin. How did these delicate structures form around Uranus? Are they remnants from the planet's past, perhaps from moons that were destroyed by collisions or gravitational interactions? This kind of speculation invites us to consider a dynamic history filled with cosmic events. Every detail, from the rings' discovery to their elusive appearance, adds to the chilling, almost supernatural aura surrounding Uranus. Moreover, the faintness of the rings makes them hard to detect without the right tools, creating a sense of hidden secrets waiting to be unveiled. This air of mystery captivates researchers and space enthusiasts alike, leading to a fascination with what lies beyond the visible spectrum. Combined with its unique rotation, cold atmosphere, and bizarre moons, Uranus's rings contribute to a story that feels just as much about exploration as it does about the unknown, cementing the planet's reputation as one of the most enigmatic in our solar system. Neptune, the distant blue planet, is known for its tumultuous atmosphere, exhibiting some of the most violent wind systems in our solar system. These winds can reach speeds much greater than those found on Earth, likening Neptune's weather to a storm on a whole different scale. This presents a fascinating challenge to scientists studying extreme weather conditions. Firstly, the sheer speed of Neptune's winds, which can exceed the velocity of sound, prompts questions about the mechanisms driving such forces far from the sun's heat. On Earth, our most turbulent weather is influenced by solar energy, with temperature differences creating winds and storms. However, Neptune sits in a much colder region, and its atmospheric patterns appear to defy our expectations. This suggests that either unknown internal heat mechanisms or unique atmospheric compositions are at play, indicating that weather dynamics could operate differently in colder planetary atmospheres compared to our own. Moreover, the complexity of Neptune's storms adds another layer of intrigue. Unlike Earth, where we primarily see cyclones and anticyclones dictated by the planet's rotation and thermal energy, Neptune's weather systems seem to have their own rules. The planet's atmosphere is a swirling mass of clouds, composed largely of hydrogen, helium, and methane, the latter giving Neptune its striking blue color. These ingredients influence how storms form, move, and evolve, often leading to massive, dark storm systems reminiscent of hurricanes but much larger in scale. Additionally, the potential for sustained weather patterns on Neptune challenges our understanding of atmospheric stability. On our planet, storms typically resolve over time, transitioning through various phases. However, Neptune exhibits storms that can persist for extended periods, raising questions about how energy is conserved and redistributed within such a massive atmosphere. This persistence may suggest a different balance of forces and energy compared to Earth, leading to new theories about atmospheric dynamics. Ultimately, studying Neptune's extreme weather invites scientists to reevaluate what we know about atmospheric science. The lessons learned from Neptune can extend beyond this icy giant, offering insights into other celestial bodies with unique weather systems, such as exoplanets. Each discovery on Neptune serves as a crucial piece in unraveling the complex puzzle of planetary atmospheres across the universe, broadening our understanding of what constitutes extreme weather conditions in a cosmic sense. The Great Dark Spot on Neptune is a massive storm, one of the most striking features of this distant planet. Imagine a colossal hurricane swirling in a breathtaking dance of winds and clouds stretched over thousands of kilometers. It exemplifies Neptune's dynamic atmosphere, characterized by intense storms and powerful winds that can reach astonishing speeds. This dark spot is created by the unique atmospheric conditions on Neptune, where strong, swirling winds interact with the planet's deep blue haze. The storm appears darker because it consists of deeper, warmer clouds that absorb sunlight, contrasting sharply with the surrounding lighter gases. The winds generate huge waves and turbulent weather patterns across Neptune's atmosphere, contributing to its eerie and dramatic planet-wide landscape. As the Great Dark Spot evolves, it reveals the violent nature of Neptune's weather. Unlike storms on Earth, which can last days or weeks, these cosmic tempests can change rapidly, sometimes disappearing altogether. Observing these transformations gives scientists valuable insights into the meteorological processes on this ice giant, enhancing our understanding of atmospheric dynamics beyond our home planet. Through this lens, the Great Dark Spot serves as a reminder of the unpredictability and beauty of nature, even in the vastness of space. It creates an otherworldly landscape that captivates the imagination, highlighting Neptune's status as one of the most fascinating planets in our solar system. Neptune, the distant eighth planet from the Sun, captivates observers with its striking deep blue color. This stunning hue is primarily a result of its atmosphere, which is rich in methane. Methane molecules absorb light in the red part of the spectrum while reflecting and scattering blue light, creating that vivid cerulean effect. As we gaze upon Neptune, this brilliant vision triggers feelings of awe. It represents the beauty and mystery of the cosmos, drawing us into the endless expanse of space. Yet alongside this admiration exists a sense of unease. Neptune is a world of extremes and unforgiving conditions, with fierce winds that can reach unimaginable speeds and violent storms that brew in its atmosphere. This beautiful planet harbors a chaotic environment that starkly contrasts its serene appearance. The very qualities that make Neptune visually enticing underscore its inherent danger. The deep blue hue symbolizes both the tranquil surface beauty of our universe and the hidden tempest lurking beneath, reminding us that even the most captivating sights can conceal peril. This duality reflects larger themes of exploration and understanding, wonders that inspire us while also challenging our limits and comprehension. Neptune's composition and atmosphere create conditions that are extremely hostile to life as we know it. The planet is primarily made up of hydrogen, helium, and methane, which form a thick atmosphere with high pressure and low temperatures. Imagine a place where the air is filled with gases that are not breathable for humans or any terrestrial organisms. The temperatures at the cloud tops can drop to several hundred degrees below freezing, making it a frigid environment that is much colder than even the harshest winter on Earth. Moreover, the atmospheric pressures on Neptune are crushing. If you were to descend into its depths, the pressure would increase dramatically with depth, far beyond what any known life forms could withstand. In addition to this crushing weight, storms on Neptune are among the most powerful in the solar system, with winds that can whip around at speeds exceeding the fastest hurricanes on Earth. These relentless winds create a chaotic atmosphere filled with swirling clouds and violent weather patterns. Another critical factor is the presence of methane in Neptune's atmosphere. While methane is often discussed in the context of potential energy sources, its existence on Neptune contributes to a chemical makeup that is not suitable for supporting life as we understand it, particularly because it does not offer the necessary elements and compounds that living organisms need to survive. The extreme cold, unbreathable gases, immense pressure, and chaotic weather on Neptune combine to form an environment that is incredibly hostile for any known life forms. The conditions are so different from Earth that they represent an insurmountable barrier to life as we know it. On the exoplanet Gliese 436b, there is a fascinating yet frightening phenomenon known as burning ice. This planet, located about 42 light-years from Earth, has extreme atmospheric conditions that create a unique form of water. Rather than existing in its typical liquid state or even as vapor, water on Gliese 436b exists as ice that melts into a liquid that does not behave like Earth's water. Instead, it burns due to the planet's intense heat and pressure, resulting in a state where this burning ice can produce unexpected hazards. This peculiar state of water, where it transitions from solid to an unusual form of liquid, leads to a frightening possibility: intense atmospheric reactions that could create conditions hostile to any potential life forms. At such high temperatures, the physical and chemical properties of substances are drastically altered. The water, under such stress, could lead to chemical reactions that generate gases or other materials not found on our planet, potentially creating toxic clouds and surface conditions that are far from habitable. Furthermore, if there were a way for any organism to adapt to these circumstances, the violent weather patterns driven by the relentless heat, including storms and tidal forces, would present insurmountable challenges. The landscape, composed of frozen substances that burn rather than bringing life-giving water, showcases an environment where survival is nearly impossible, painting a picture of an alien world that is both scientifically intriguing and ominously inhospitable. Gliese 436b presents a fascinating case study in planetary dynamics, primarily because of its unique gravitational interactions. This exoplanet orbits a star that is significantly smaller and cooler than our Sun, yet it boasts a density suggesting it is predominantly made up of water in a strange form. The gravitational pull on Gliese 436b is intense due to its proximity to its host star. Being very close means the planet experiences incredible forces that cause extreme atmospheric conditions. The pressure exerted by its own gravity compresses the water so much that it exists in a state resembling ice but behaves like liquid. This phenomenon leads to the formation of what could be described as hot ice, creating a surface that is unrecognizable compared to Earth's terrestrial environments. Moreover, the high temperatures from the nearby star contribute to relentless weather patterns. Intense winds whip across the planet due to rapid atmospheric movements, while the warped pressure conditions create ceaseless storms that could dwarf even the most extreme weather events found on Earth. The combination of extraordinary heat, crushing pressure, and dynamic atmospherics leads to a landscape rife with challenges. In the vastness of its atmosphere, exotic phenomena might occur, such as vaporized materials being propelled under immense heat and pressure, possibly resulting in the mental image of a planet wrestling with its own elemental chaos. Gliese 436b encapsulates the concept of a celestial body where life, as we know it, would find survival almost unimaginable amid such unusual and terrifying planetary conditions. Gliese 436b presents a fascinating yet extreme case when it comes to the conditions on exoplanets. This distant world is an example of a hot Neptune, a type of planet that has a gaseous atmosphere and is significantly closer to its star compared to our own Neptune. The high pressure found on Gliese 436b stems from its substantial gravitational pull, which compresses its atmosphere densely. This creates a thick layer of gases that trap heat, contributing to an intense greenhouse effect. The greenhouse effect is a natural phenomenon that allows a planet to retain heat from its star. However, on Gliese 436b, this process is exaggerated due to its proximity to its host star, resulting in surface temperatures soaring to levels that would be unmanageable for any known form of life. Essentially, the planet is undergoing extreme heat retention, so while our Earth enjoys a balanced atmosphere, Gliese 436b finds itself in a locked cycle of oppressive heat and pressure. Additionally, the atmospheric composition plays a crucial role. The gases present can lead to a scenario where the environment is not just inhospitable due to temperature, but also because of chemical unavailability for life as we know it. The crushing pressures combined with relentless heat create conditions that would be lethal, effectively rendering the planet uninhabitable. In the face of such environmental extremes, any potential for life is extinguished, making Gliese 436b a stark example of a world where the pressures and temperatures soar beyond survivability. Gliese 436b is a fascinating exoplanet that challenges our understanding of what planets can be like. This distant world lies about 33 light-years away from Earth and is classified as a hot Neptune. It is not just its size that intrigues scientists, but the extreme conditions present on this planet that create a striking contrast between ice and fire. On Gliese 436b, temperatures soar high enough to infer that the atmosphere is in a molten state. However, the planet's interior also harbors pockets of ice, which shouldn't exist under such heat. This peculiar combination occurs due to the immense pressure found beneath the planet's atmosphere, which effectively transforms water into a form of ice that behaves quite differently than what we're familiar with on Earth. Scientists wonder how these conditions can coexist, leading to realms of inquiry about chemical reactions, material properties, and the limitations of planetary science. The idea of a planet that is both ice and fire instills a sense of fearful curiosity among scientists because it defies standard planetary formation theories. It forces them to reconsider the possibilities of life and the diverse environments that could exist elsewhere in the universe. This mix of extreme conditions leaves many questions unanswered. What forms of chemistry thrive there, and could there be unknown processes at work? Each of these inquiries opens the door to new theories and deeper explorations, making Gliese 436b a unique subject for researchers who seek to understand both the nature of planets and the very fabric of our universe. LHS 1140b, an exoplanet located just a short distance from its host star, experiences extreme environmental conditions due to this close proximity. This planet orbits a red dwarf star, which is smaller and cooler than our Sun, but it is still positioned close enough that the gravitational pull significantly affects its atmosphere and surface. Being near its star means that LHS 1140b receives a concentrated amount of stellar radiation, which can lead to intense heating of its surface. This influx of energy results in a temperature increase that can vary greatly, depending on the planet's rotation and atmospheric conditions. If the planet has a thick atmosphere, it could trap heat, creating a runaway greenhouse effect similar to what we see on Venus, though the specific outcomes on LHS 1140b are still unknown. Moreover, red dwarf stars, including the one orbiting LHS 1140b, can exhibit stellar flares, large bursts of radiation that can drastically impact a planet's atmosphere. These flares may strip away any atmosphere that the planet possesses, making it difficult for life as we know it to exist. The combination of close proximity to a star with frequent and unpredictable stellar events leads to a hostile environment with intense radiation, potential atmospheric loss, and extreme temperature variations. Ultimately, the conditions on LHS 1140b are a fascinating blend of heat, energy, and potential atmospheric dynamics, raising intriguing questions about the planet's ability to support any form of life and how such extremes reshape its landscape over time. The study of LHS 1140b provides essential clues about the similarities and differences between potentially habitable worlds and our own Earth. The atmosphere of LHS 1140b presents a compelling blend of both dread and intrigue, largely due to its unique characteristics. This planet is classified as a super-Earth, meaning it is larger than our own but may be capable of retaining a significant atmosphere. The density of its atmosphere raises fascinating questions about its composition and the potential for supporting life, as well as the challenges it poses. On one hand, scientists find intrigue in the idea that a thick atmosphere could indicate the presence of a diverse range of gases. This could include elements essential for life, similar to how our own atmosphere contains oxygen and nitrogen. The potential for clouds, weather patterns, and even storms adds another layer of fascination, suggesting that LHS 1140b might experience complex climatic systems. Understanding the conditions within such an atmosphere could offer clues about planetary formation and the possibilities of extraterrestrial life. On the flip side, the sheer density of LHS 1140b's atmosphere could also indicate extreme pressure and hostile conditions. If the atmosphere is rich in carbon dioxide or other greenhouse gases, the temperatures may be scorching, making it inhospitable to life as we know it. Furthermore, the atmospheric pressure would crush any familiar organism, rendering survival on its surface virtually impossible. The very features that make it an interesting target for exploration simultaneously pose significant risks and challenges for any potential missions to the planet. Ultimately, LHS 1140b serves as a striking example of how the mysteries of alien worlds can evoke both anxiety and excitement. The study of such planets allows scientists to address fundamental questions about the universe, how atmospheres evolve, what they reveal about planetary history, and whether the search for life beyond Earth will one day lead us to places that are both fascinating and frightening. LHS 1140b is an intriguing exoplanet that has sparked conversations about the potential for life beyond our own planet. Its size is significant, as it is classified as a sub-Neptune, meaning it lies between Earth and Neptune in terms of dimensions and density. This relatively modest size suggests that it could possess a solid surface rather than being a gas giant like Jupiter. What makes LHS 1140b particularly exciting is its position within the habitable zone of its star. This is the region where conditions may be just right for liquid water to exist, a critical ingredient for life as we know it. The presence of water is essential because it acts as a solvent for biochemical reactions, provides a medium for transporting nutrients, and helps regulate temperature. If LHS 1140b has retained enough heat and possesses the right atmospheric conditions, liquid water could indeed exist on its surface, dramatically increasing its potential to support life. Furthermore, the atmosphere plays a vital role in determining habitability. If LHS 1140b has a thick atmosphere, it could protect water from evaporating and maintain suitable temperatures conducive to life. On the other hand, a thin atmosphere might expose water to harsh radiation and temperatures that would hinder the development of any biological processes. Together, the size of LHS 1140b and its potential for water reshape our understanding of habitability. Instead of only seeking planets that are Earth-like, we can re-evaluate rocky planets of different sizes and compositions that may harbor environments capable of supporting life. It challenges us to broaden the definition of habitable worlds, revealing that life might thrive in unexpected places beyond the familiar parameters established by our own solar system. In the quest to discover life elsewhere, LHS 1140b stands out as a promising candidate, sparking curiosity and wonder about the possibilities that lie beyond. LHS 1140b is an intriguing exoplanet located in the habitable zone of its parent star, which is a region where conditions could allow for the existence of liquid water. What makes this planet particularly surprising is its substantial size and mass, characteristics which typically lead scientists to expect a very different environment. Most exoplanets found in habitable zones are similar in size to Earth, often categorized as super-Earths or smaller worlds. However, LHS 1140b stands out because it is classified as a larger rocky planet, potentially bearing dense materials that could suggest a more challenging environment for life. Its significant gravitational force may create a thick atmosphere, possibly rich in greenhouse gases, which could push temperatures well beyond what life as we know it would tolerate. Another unexpected element is its proximity to a red dwarf star, which is known for lower luminosity compared to stars like our Sun. This leads to a cooler habitable zone situated much closer to the star, requiring planets like LHS 1140b to be relatively close to avoid freezing temperatures. This intimate relationship with its star and its larger size challenges conventional wisdom about what kinds of planets can exist as habitable environments. Additionally, the characteristics of red dwarf stars imply a greater likelihood of stellar flares and radiation bursts, which could bombard planets nearby. These conditions typically would hinder the potential for habitability, leading researchers to question whether LHS 1140b could maintain stable conditions on its surface or possess a protective atmosphere. These facets of LHS 1140b defy the expectations dictated by our understanding of exoplanet conditions and formation, allowing scientists to reconsider the parameters of habitability and the diverse nature of worlds that might support life. Observing this planet further can provide invaluable insights into how we define habitability in an ever-expanding universe. Kepler-69c is an intriguing exoplanet, primarily due to its unusual orbit that raises interesting questions about potential seasons and climates. This planet orbits a star much like our Sun, but its orbital path is not a simple circle. Instead, it follows a more eccentric shape, which adds complexity to how it experiences changes in temperature and light throughout its year. Imagine a planet that moves along its orbit in a way that brings it closer to its star at certain times and farther away at others. This wobble not only changes the amount of sunlight it receives, but it also means that the intensity and distribution of heat are unevenly spread across its surface. As Kepler-69c swings closer to its star, it could experience extremely hot temperatures, while during its farther points, the climate may become much cooler. But there's more at play than just distance from the star. The tilt of Kepler-69c, much like Earth's axial tilt, also contributes to seasonal changes. If the planet has a significant tilt, some regions might face the sun more directly during part of its orbit, leading to intense sunlight and heat, while on the opposite side of its journey, these same areas might experience long stretches of darkness and cooler conditions. This combination of orbital eccentricity and axial tilt can lead to unpredictable and extreme seasonal variations. These fluctuations could create a climate that's not only diverse across the planet, but also potentially unsettling for any forms of life that may exist there. Picture a world where one season can swing from sweltering heat to frigid cold in a relatively short period. The rapid changes can impact weather patterns and could lead to storms or climate systems that are far more chaotic than those we experience on Earth. The fascinating interplay of these factors paints a picture of Kepler-69c as a planet where understanding its climate would be both essential and challenging, offering a glimpse into the diverse possibilities of planetary atmospheres beyond our own. Kepler-69c is an exoplanet located over 250 light-years away from Earth, a distance that presents a unique set of challenges and wonders. Being so far away limits our ability to study this intriguing world in detail. The vastness of space means that even the most advanced telescopes can only capture faint glimpses of its features. We rely on indirect methods to learn about its atmosphere, potential surface conditions, and even the possibility of life forms. The inability to send a spacecraft there compounds this problem, as we can only rely on data collected from afar, which often lacks the depth necessary for comprehensive analysis. This substantial distance also stirs a mix of curiosity and apprehension. The unknown elements surrounding Kepler-69c and exoplanets like it spark the imagination and provoke thoughts about what mysteries the cosmos holds. The potential of discovering new life or entirely different ecosystems tantalizes scientists and enthusiasts alike, yet it's intertwined with an eerie fear of the unknown. What if the conditions are vastly different from what we expect? Or what if they carry threats we are yet to comprehend? This duality of inspiration and fear reflects humanity's broader relationship with the universe, an endless quest for knowledge overshadowed by the vulnerabilities that come with all things unexplored. The immense distance to Kepler-69c shapes our understanding by setting strict limits on observation and research, creating barriers to definitive knowledge. Yet it also fuels our desire to learn, driving us to reach ever further into the cosmos, fascinated by what we might discover in that deep and dark expanse. Kepler-69c is an intriguing exoplanet that has sparked discussions about the possibilities of life beyond Earth. Positioned in its star's habitable zone, where conditions could allow for liquid water, it offers a glimmer of hope for life. However, this prospect pairs with significant dangers that challenge our understanding of habitability. The first point of potential lies in its size. Kepler-69c is classified as a super-Earth, suggesting it has a greater mass than our planet. This dimension could mean that it has enough gravity to hold a thick atmosphere, potentially rich in essential gases like oxygen and carbon dioxide, which are crucial for supporting life as we know it. If present, liquid water could exist, creating environments similar to Earth's oceans or lakes where life might thrive. On the flip side, the dangers emerge primarily from its host star, a type of star known as a K-dwarf. This type of star, while stable, is also known to emit bursts of radiation and solar flares. Increased levels of radiation could strip away the atmosphere, rendering the planet inhospitable over time. Furthermore, any potential atmosphere might be unsteady or lacking in the right balance of gases, making it challenging for life to develop or sustain itself. Another concern revolves around what we don't know about its surface conditions. Kepler-69c might possess extremes of temperature or hostile geological activity resulting from strong gravitational forces, creating a landscape that varies wildly. Such conditions would make it challenging for organic life to emerge, as survival would depend heavily on specific temperatures and geological stability. While Kepler-69c showcases features that breathe potential into the search for extraterrestrial life, including its placement in a habitable zone and its possible atmospheric composition, it simultaneously presents dangers that could inhibit such life from ever flourishing. Its story is a vivid reminder that the universe harbors both hope and uncertainty. Kepler-69c is a distant exoplanet that stirs both intrigue and apprehension as it bears some resemblance to Earth. It orbits a star similar to our Sun and is located within the habitable zone, a sweet spot where conditions might be suitable for liquid water, a fundamental ingredient for life as we know it. This connection to Earth fuels a desire to explore, yet also casts a long shadow of uncertainty. When we compare Kepler-69c to our home planet, it becomes a canvas for speculation. The potential for Earth-like qualities suggests it could harbor life, sparking dreams of discovering extraterrestrial beings. However, this very similarity amplifies the sense of menace. What if life exists there, but it is drastically different from what we know, hostile or deeply alien in nature? The prospect of encountering a world that mirrors our own yet operates under entirely different rules sends shivers down the spine. Furthermore, the factors that define habitability, such as atmospheric composition and climate, remain unknown for Kepler-69c. This uncertainty only adds to the mystique. Could its atmosphere be thick and suffocating, concealing deadly gases? Or perhaps it harbors extreme weather patterns that could challenge even the most adaptable life forms. The juxtaposition of the familiar and the unknown creates a tense narrative, a beautiful planet that might just hold its own set of dangers. The allure of Kepler-69c lies in its potential to reflect our hopes and fears. By mirroring Earth in some aspects, it invites us to dream while simultaneously warning us of the complexities that lie beyond our knowledge. Each piece of information we discover about this enigmatic world shapes our understanding of what it means to seek life beyond our own blue planet. The TRAPPIST-1 system is fascinating not just because of its rarity, but also due to the intricate dance of its planets, particularly TRAPPIST-1e. This world orbits a small, cool star at a distance that places it in a region known as the habitable zone, where conditions could allow liquid water to exist. However, the orbital dynamics of the planets contribute to an environment that may be perilous for any potential life. Firstly, all 7 planets in the TRAPPIST-1 system are locked in a gravitational ballet influenced heavily by each other's presence. This gravitational interaction leads to a phenomenon known as resonant orbits, where the orbital periods of the planets are closely linked. In simpler terms, the movement of one planet can significantly affect another, creating a tug-of-war in their paths. For TRAPPIST-1e, this means that its own orbit is altered by the gravitational pull of its neighboring planets, which could destabilize the climate over long periods. Moreover, TRAPPIST-1 is classified as an ultra-cool dwarf star, which generates most of its light in infrared wavelengths. Such stars can be prone to strong stellar flares, explosive bursts of radiation that can strip nearby planets of their atmospheres over time. For TRAPPIST-1e, proximity to its star makes it vulnerable to these energetic outbursts. The intensity of radiation could create an inhospitable environment, blasting the surface with extremes that would challenge the very existence of water and potential life. Additionally, the lack of a significant magnetic field, which many larger planets possess to protect against stellar radiation, might expose TRAPPIST-1e to even greater risks. Without such a shield, any atmosphere that may exist could be subjected to erosion by the stellar winds, rendering the planet increasingly barren. Taken together, these factors, gravitational interactions pulling TRAPPIST-1e into unpredictable orbits, vulnerability to stellar flares, and lack of protective magnetic fields, culminate in a precarious environment. While TRAPPIST-1e sits within a potentially habitable zone, the challenges posed by its orbital dynamics and cosmic setting make it a hostile place for the emergence or sustainability of life as we know it. TRAPPIST-1e stands out in the search for extraterrestrial life due to its eerie yet captivating characteristics. This exoplanet resides in the habitable zone of its star, where conditions could potentially allow for liquid water to exist, a crucial element for life as we know it. Its surface might be marked by vast oceans, delivering an environment reminiscent of Earth's early days, teeming with the potential for biological processes to take root. However, the atmosphere and surface conditions present daunting challenges. Being tidally locked to its star, one side of TRAPPIST-1e experiences perpetual daylight, while the other remains in constant darkness. This stark division could lead to extreme temperature fluctuations, creating environments that might be inhospitable for many known life forms. On the sunlit side, relentless radiation from a cooler star can strip away protective atmospheric layers, while the dark side could plunge into extreme cold, complicating the possibility of sustaining life. Moreover, the gravitational influence of neighboring planets in the TRAPPIST-1 system may introduce additional volatility. These gravitational effects could cause atmospheric and geological changes that make the environment less stable. Yet, despite these frightening challenges, they also present a frontier for scientific exploration. Researchers are keen to understand how life might adapt to such unusual and harsh conditions, pushing the boundaries of our knowledge about where and how life could exist in the universe. Thus, while TRAPPIST-1e might evoke feelings of unease due to its extreme environment, it serves as an exciting opportunity for astrobiologists. The quest to uncover whether life could improbably survive there invites questions about the resilience of living organisms and offers insights that could redefine our understanding of life's possibilities beyond Earth. The TRAPPIST-1 system, with its 7 Earth-sized planets orbiting a cool star, offers a tantalizing glimpse into the possibility of interplanetary exchanges. This idea sparks both excitement and apprehension. On one hand, the prospect of communications or even travel between these planets ignites hope for discovering new forms of life, diverse ecosystems, and innovative technologies. If these planets host conditions favorable to life, it could lead to unprecedented cooperation and collaboration among intelligent beings, fostering a shared pursuit of knowledge and discovery that could benefit all involved. Conversely, this potential also brings a sense of fear. The universe is unpredictable, and the realities of interplanetary life may not mirror our optimistic visions. Differences in societal structures, resource competition, or even cultural misunderstandings could escalate tensions. There's also the possibility of pandemics. Diseases from one world could spread to another, decimating populations without any defenses. Furthermore, we know little about the moral implications of interacting with potentially sentient beings. Would our actions reflect benevolence or domination? Exploring these planets could ultimately unveil both the wonders of the universe and the darker sides of our nature. This duality, where hope for connection and discovery exists alongside the fear of unknown consequences, defines our fascination with the TRAPPIST-1 system as we ponder the future of humanity's role within the galaxy. TRAPPIST-1e is a captivating subject in the quest for potentially habitable exoplanets, as it sits within the habitable zone of a star not too far from our own solar system. This zone is a region around a star where conditions could allow liquid water to exist on a planet's surface, a key ingredient for life as we understand it. What makes TRAPPIST-1e even more intriguing is its size and composition, similar to that of Earth, hinting at the possibility of a rocky surface. Its orbit around a cool dwarf star means it experiences different conditions compared to Earth. Despite this, simulations suggest that it could retain an atmosphere conducive to life. However, this planet presents challenges. Being close to its star might expose it to intense radiation and gravitational tidal forces, factors that could strip away its atmosphere. Researchers consider whether, even in such harsh conditions, TRAPPIST-1e might harbor life. By studying this planet, scientists hope to understand more about how life might adapt or survive in environments that are vastly different from our own. The ongoing exploration of TRAPPIST-1e and its system deepens our understanding of the potential for life beyond Earth, enriching the narrative of our search for extraterrestrial beings. Potential oceanic worlds like Kepler-62f offer a fascinating duality of exploration prospects, igniting both fear and excitement among scientists and dreamers alike. At first glance, Kepler-62f presents an alluring vision of vast, hidden oceans beneath an atmosphere thick enough to support complex weather systems. This creates a tantalizing possibility of rich ecosystems teeming with life, similar to the biodiverse environments found in Earth's own oceans. However, the thrilling prospect of discovering extraterrestrial life is offset by significant dangers that arise in such extreme environments. The oceans of these exoplanets could exist under intense pressures, akin to the crushing depths of Earth's Mariana Trench, creating challenges for any exploratory missions. These conditions might render robotic explorers obsolete and present hurdles for human missions. The equipment designed to withstand such pressure would need to be exceptionally robust and innovative. Moreover, the composition of the oceans remains a significant unknown. The water on these planets might not be just plain H2O, but could contain other elements or compounds that are toxic or corrosive, adding another layer of risk to the exploration efforts. The dynamic climate on these worlds, potentially driven by alien atmospheric phenomena, adds unpredictability. Storms might rage across alien oceans, obscuring visibility and disrupting any missions attempting to study the surface or dive beneath it. Yet these risks only fuel the excitement surrounding such oceanic worlds. Uncovering the mysteries of these alien oceans could revolutionize our understanding of biology, chemistry, and the conditions necessary for life to flourish. In striving to understand the nature of these underwater realms, we might discover life forms that are entirely different from anything we've encountered, broadening our perspective on what it means to be alive in the universe. The combination of peril and promise in exploring potential oceanic worlds like Kepler-62f holds an irresistible allure for scientists and the public alike. The chance to unveil the secrets of alien oceans beckons us to push the boundaries of technology, innovation, and human courage. Thus, Kepler-62f stands as a symbol of our quest to understand whether we are truly alone in the cosmos, sparking both trepidation and wonder in equal measure. Kepler-62f orbits a distant star that is cooler and smaller than our own Sun, classified as a K-dwarf star. Because of this, the sunlight reaching Kepler-62f is significantly fainter. Imagine standing in a dimly lit room instead of basking under the bright sun. That gives you a sense of how weak the light would be on Kepler-62f. This reduced sunlight means that any potential life forms would have to adapt to a much lower level of light energy. Photosynthesis, as we know it on Earth, relies on ample sunlight for plants to convert light into energy. In a dim environment, it could be challenging for any plant-like organisms to thrive. If they did manage to evolve, they might develop darker pigments to absorb as much light as possible, but such adaptations come with limitations. Additionally, the faint sunlight would likely result in cooler temperatures. If the planet's atmosphere is not thick enough to trap heat effectively, it could lead to chilling conditions, making it hard for life forms to maintain a stable internal temperature. For organisms accustomed to warmth, like most on Earth, this could prove to be a significant hurdle for survival. Moreover, the limited energy from the faint light would affect the entire ecosystem, impacting food chains and nutrient cycling. Simple organisms might struggle to extract sufficient energy, resulting in fewer resources for larger, more complex life forms. Thus, living on Kepler-62f could present life with challenges akin to living in a constant twilight. Sustaining energy, warmth, and the complex interactions necessary for flourishing would all be daunting prospects. Kepler-62f, an intriguing exoplanet located within the habitable zone of its star, sparks the imagination with its potential atmosphere. Speculations surrounding its atmospheric composition heighten both its mystery and intimidation. Picture this distant world, larger than Earth, orbiting a star cooler than our Sun. Scientists have wondered whether Kepler-62f could harbor an environment rich in water vapor or other gases essential for life as we know it. Imagining an atmosphere filled with thick clouds of mysterious origins creates an unsettling yet fascinating picture. These clouds could imply a variety of conditions, ranging from those supportive of life to extreme environments hostile to it. If Kepler-62f were shrouded in dense fog, it might obscure surface features, making it difficult for astronomers to determine the planet's geography or geological processes. Such obscurity invites curiosity, but also an air of dread about what might lie beneath. Moreover, speculations about its atmospheric pressure and temperature offer additional layers of complexity. An atmosphere rich in carbon dioxide could indicate a greenhouse effect, potentially leading to scorching temperatures that would render the surface inhospitable. In contrast, a frigid climate could mean that any water present is frozen, limiting the possibilities for life. These contrasting scenarios contribute to the planet's inherently nervous nature. Floating in the vastness of space, its atmosphere holds secrets that are tantalizing yet foreboding. The combination of uncertainty and endless possibilities makes Kepler-62f not just another planet, but a captivating enigma. As we contemplate the unseen forces shaping this world's atmosphere, we are left with questions that linger in the air, propelling our quest for understanding beyond the fringes of our own solar system. Kepler-62f stands out as a captivating world located in a star system about 1,200 light-years away from Earth. Described as a super-Earth, it orbits within its star's habitable zone, where conditions may permit the presence of liquid water, an essential element for life as we know it. For exoplanet hunters, Kepler-62f is a dream come true because it represents the potential for discovering alien life and understanding how diverse planetary systems can be. The mere possibility that this planet could harbor a thriving ecosystem ignites the imaginations of scientists and enthusiasts alike. However, this dream can quickly turn into a nightmare when considering the planet's actual conditions. Kepler-62f is larger than Earth, raising questions about its atmosphere and gravity. If it has a thick atmosphere, it could create a runaway greenhouse effect, leading to temperatures far beyond human tolerance. Alternatively, a thin atmosphere might expose any surface conditions to the cosmos, resulting in harsh climates. Such uncertainties make it a challenge to assess whether Kepler-62f is truly promising or potentially inhospitable. Kepler-62f embodies the duality of hope and concern in the search for exoplanets. It represents the thrilling prospect of discovering life beyond our world, while simultaneously reflecting the harsh realities of hostile environments that may deter our aspirations of colonization or understanding other forms of life. This complexity fuels both excitement and caution among exoplanet hunters navigating the vast expanse of the universe. Saturn is often celebrated for its majestic and intricate system of rings, which set it apart from all other planets in our solar system. These rings, composed of countless tiny ice particles and dust, create a dazzling spectacle that catches the eye of anyone observing the planet. Each ring orbits Saturn at varying distances and speeds, and their complex structure can change over time due to gravitational interactions. This dynamic play of light and shadow adds to Saturn's enigmatic allure, capturing the imagination of astronomers and casual observers alike. However, beneath this stunning exterior lies a planet with tumultuous and sometimes violent weather systems, which contribute to its unnerving nature. Saturn is known for its intense storms, including raging winds that can whip around the planet at astonishing speeds. Some storms are massive, with lightning strikes that can be millions of times more powerful than those on Earth. The atmosphere is layered, featuring different bands that shift in color and intensity, revealing a world that is constantly in motion. The combination of the ethereal beauty of its rings and the chaotic atmosphere creates a sense of contradiction in Saturn's character. It embodies both grace and danger, drawing observers into its splendor while reminding them of the unpredictable forces operating within. This balance of breathtaking visuals and tumultuous weather reinforces Saturn's reputation as a giant whose surface masks deeper, unsettling complexities. The striking beauty of Saturn enchants us, yet its fierce storms and ever-changing atmospheres remind us of the raw power of nature in the cosmos. The hexagonal storm patterns on Saturn are one of the most captivating features of the planet's atmosphere. Picture a gigantic, swirling giant displaying a unique geometric pattern, a six-sided shape that measures thousands of kilometers across. This phenomenon occurs at Saturn's North Pole and is a dazzling display of the planet's complex atmospheric dynamics. These hexagonal storms form as the planet's extremely fast winds collide within its thick atmosphere. Saturn experiences powerful jet streams, where winds can reach staggering speeds. When these winds blow around the North Pole, they interact in a way that creates the distinct hexagonal shape. The sheer size of the hexagon is astonishing. It could easily encompass multiple Earths within its borders. The stability of this hexagonal pattern is equally intriguing. Unlike the chaotic nature of many storms on Earth, which eventually dissipate or transform, Saturn's hexagon appears to remain fixed in place for decades and possibly longer. This suggests a unique balance of forces at play, as the relentless winds maintain the structure against the shape-shifting reality of atmospheric systems. Examining the hexagon also reveals the presence of other atmospheric elements, like the intriguing storms that form at its edges. Some of these storms become enormous, showcasing sudden eruptions of activity that add to the planet's dynamic weather patterns. The interactions between these storms and the hexagon itself create a mesmerizing ballet of meteorological conditions that scientists are eager to study. This unique combination of geometry, stability, and dynamic weather illustrates not just the complexity of Saturn's atmosphere, but also highlights the differences between gaseous giants and terrestrial planets like Earth. By studying such patterns, scientists gain valuable insights into the underlying physical processes that govern planetary atmospheres, not only on Saturn but across the universe. The hexagonal storm pattern stands as a mesmerizing testament to the mystifying and beautiful forces at work in Saturn's atmospheric ballet. Saturn, with its breathtaking rings and striking coloration, captivates the imagination like few other celestial bodies. Its sheer size is almost overwhelming, as it is the second largest planet in our solar system. Imagine a sphere that could fit more than 1,000 of Earth's globes within its vast expanse. This immense scale serves as a reminder of the universe's grandeur, igniting a mix of awe and reverence. The planet's beauty is equally compelling. The rich golden hues of its atmosphere, streaked with subtle bands of color, are mesmerizing. These vibrant shades are created by varying gases in the atmosphere and complex chemical reactions, capturing light in ways that render the planet almost ethereal. Yet this beauty is tinged with a sense of mystery. The rings, composed of ice and rock particles, create a halo effect that is simultaneously elegant and stark, evoking a feeling of both wonder and foreboding. As we gaze upon Saturn, we are reminded of the vast forces that have shaped it over billions of years. Its presence commands respect. The storms raging through its atmosphere can be ferocious, and the planet's powerful gravitational pull can disrupt orbits far beyond its reach. This duality of beauty and potential danger creates a tension that evokes a sense of ominous grandeur. Saturn stands as a colossal monument to the power of nature and the intricate tapestry of the cosmos, inviting us to ponder our place within it. Saturn's magnetic field is a captivating force that significantly influences its moons and the surrounding space environment. Picture a gigantic bar magnet with Saturn at its center. This magnetic field is generated by the motion of metallic hydrogen within Saturn's interior, creating a strong magnetic domain that envelops the planet. The influence of this magnetic field can be especially noted in the interaction with Titan, Saturn's largest moon. Titan possesses its own atmosphere, which is primarily composed of nitrogen, and Saturn's magnetic field plays a key role in shaping this environment. As charged particles from the solar wind, streams of energetic particles emitted by the sun, approach Titan, the magnetic field creates a protective bubble, or magnetosphere, that prevents these particles from directly impacting Titan's surface. However, this protection does not come without consequences. The interaction between Saturn's magnetic field and Titan's atmosphere causes the upper layers of the atmosphere to become ionized, releasing charged particles. These particles can then be trapped within the Moon's magnetic environment, creating a continuous cycle of energy and influencing the atmospheric chemistry. Furthermore, Saturn's magnetic field extends well beyond its rings and moons, interacting with the space environment and other celestial bodies in its vicinity. This interaction leads to the creation of radiation belts made up of high-energy particles, similar to Earth's Van Allen belts. The moons within these belts can experience varying levels of radiation exposure, particularly those closer to the planet. This exposure can affect their surface chemistry and possibly their potential for hosting life. The magnetic field also contributes to the dynamic environment of Saturn's rings. Charged particles from the rings can interact with the magnetic domain, resulting in phenomena such as auroras on Saturn itself. These colorful displays occur at the planet's poles due to the inflow of energized particles from the magnetic field, showcasing the interconnectedness of Saturn, its rings, and its many moons. Overall, Saturn's magnetic field acts like a cosmic puppet master, influencing the behavior and characteristics of its moons and shaping the intricate dance of particles in the space surrounding this majestic planet. GJ 504b is a fascinating exoplanet that captures the attention of astronomers for several compelling reasons. First and foremost, its young age is striking. At approximately 500 million years old, GJ 504b is still in what can be considered its early stages of formation compared to other planets in our universe. This youth indicates that it may possess characteristics that are not fully matured and can reveal valuable insights about planetary development processes. Adding to the intrigue is GJ 504b's remarkably hot surface. This heat suggests that the planet still retains heat from its formation, a phenomenon known as residual thermal energy. The extreme temperatures raise questions about the atmospheric composition and weather patterns this young world experiences. The idea of a planet with such intense heat challenges astronomers' understanding of how planets evolve over time. What's unsettling for scientists is the possibility of unearthing unexpected phenomena associated with young exoplanets like GJ 504b. For instance, the interactions between its atmospheric conditions and its heat could lead to unique weather systems or chemical compositions not seen elsewhere. Moreover, the prospect of young planets having retained enough energy to influence their surroundings pushes the boundaries of current theories about planetary atmospheres and geology. GJ 504b serves as a tantalizing case study for astronomers. Its young age and heated surface not only provide an opportunity to explore the dynamic processes of planetary evolution, but also challenge existing models, compelling scientists to rethink what they know about planets beyond our solar system. GJ 504b stands out in its cosmic neighborhood, not just due to its size, but because of its striking color and temperature differences. Picture a distant world that appears a fiery pink against the backdrop of the dark universe. This vibrant hue is a direct result of its heat. GJ 504b is a gas giant, radiating warmth that creates a distinctly bright visual. The intense, warm color contrasts sharply with colder celestial objects, evoking an unsettling aura that captivates observers. The atmosphere of GJ 504b itself is likely thick with clouds composed of various chemicals. These clouds filter light in such a way that they enhance the planet's vivid coloration, creating a dramatic appearance that is both captivating and slightly ominous. Such striking features elicit a sense of fear or unease, as it challenges our familiar understandings of habitability and safety in space. The notion of a vibrant yet hostile planet invites both intrigue and caution, as its brilliance suggests an environment that is at once spectacular and foreboding. Moreover, this planetary body is positioned far from its sun, making its inherent glow and colorful surface all the more mysterious in the vastness of space. The combination of a warm atmosphere, unusual color, and distant placement generates a sense of isolation, an enigmatic presence lurking in the depths of the cosmos. GJ 504b's aesthetics, through vivid contrasts of color and temperature, create an atmosphere of both wonder and apprehension, illustrating how even the most beautiful celestial bodies can harbor an undercurrent of fear. GJ 504b is a fascinating example of the dynamic processes involved in planet formation. Located in the constellation of Virgo, this exoplanet is a gas giant, much like Jupiter, but it orbits a star that is considerably younger than our Sun. This youthful setting presents a unique opportunity to observe the conditions that are actively shaping such worlds. In the early stages of planetary formation, dust and gas in a protoplanetary disk coalesce to form larger bodies. As GJ 504b evolves, it shows us how these processes continue over time. The planet's atmosphere fluctuates due to a combination of factors, including the heat generated from its formation and the ongoing gravitational interactions with other bodies in the disk. This constant state of flux reflects the chaotic nature of planet formation, where collisions, mergers, and the accretion of material lead to a wide variety of physical environments. GJ 504b's temperature is notably high, which indicates that heat from its formation has not yet dissipated. This excessive warmth allows for the retention of lighter elements like hydrogen, contributing to its gaseous makeup. As planetary atmospheres evolve, they undergo significant changes. Clouds may form and dissipate, and the composition can shift as different elements and compounds interact. The relationship between temperature and atmospheric chemistry is critical, as it dictates whether certain materials will condense into clouds or remain as gaseous forms. Furthermore, the conditions on GJ 504b suggest ongoing interactions with nearby material in the protoplanetary disk, showcasing the gravitational dynamics at play. These interactions can result in the transfer of angular momentum and influence the planet's orbit, potentially impacting its evolutionary trajectory. For instance, if GJ504b were to encounter larger bodies within the disk, it could absorb mass, altering its size and atmospheric characteristics while also affecting the disk's structure. Thus, GJ504b serves as a living laboratory where the conditions of planet formation are not only reflected in its existence, but are actively shaping it. The complexities of its atmosphere, temperature, and interactions highlight just how precarious the processes of planet formation can be and remind us that even in the distant cosmos, the art of creating worlds is a turbulent and ongoing saga. GJ504b, an exoplanet orbiting the star GJ504, presents a fascinating anomaly in our understanding of planetary systems. Unlike the gas giants found in our own solar system, GJ504b is remarkably large and unusually colored, appearing as a vibrant pinkish hue. This striking visual suggests a very different kind of atmospheric composition and temperature regime than what we typically expect. In most known planetary systems, planets form in a disk of gas and dust around their parent stars, leading to a range of sizes and compositions that align with their distance from the star. Closer planets often become rocky, while those further out might accumulate more gas. However, GJ504b, located farther from its star than Neptune is from our Sun, challenges this model. Its mass suggests it should have formed more like a gas giant early in the universe's formation, yet its formation mechanisms are still a topic of active research. Moreover, GJ504b's temperature is significantly lower than that of similar-sized planets in our solar system. It's believed to be around a similar warmth to some brown dwarfs, which blurs the line between planets and stars. This raises intriguing questions about the processes that lead to the formation of such bodies. Could they form through collapse and condensation like stars, or might they arise from the aggregation of material in a less conventional manner? This discovery forces astronomers to reconsider the diversity of planetary systems and the factors that govern their evolution. GJ504b exemplifies the potential for unique and unexpected outcomes in the cosmos, suggesting a wider variety of planetary types may exist than our traditional models have accounted for. Imagine the implications of finding more such planets. It could lead us to redefine our understanding of what a planet can be and how diverse our universe truly is.